The demand for travel has decreased, right? So
yeah. I have not left my home since when I think, if not mistaken, 17th of March.
oh, okay. So I have
So
done
almost
some
9 months now. 9 months.
almost 9 months. That's a long period for a
Yeah.
person like you who used to be at so many places.
No, I did inspections virtually. Many places. No, I was supposed to go there. I said, no, I'm not coming. You want me? I will do virtually, and they agreed.
Makes sense. Makes sense.
हेमंत, माझं मीटिंग आहे आता चालू. ठीक आहे, माझी आता मीटिंग आहे नीरी बरोबर. 1 तासानंतर मी तुम्हाला फोन करतो. ओके ओके ओके.
So good to see you after a really long time. I think
Yeah, indeed. Yeah, we miss you in Mumbai.
yes, I do. Whatever you may say, Mumbai is very vibrant compared to any other places. Some people may not like this comment.
No. It is a fact. It is a fact. Mumbai is the most vibrant city, and once people come in, no, they don't leave.
Yeah. True. So Sadhna, we can start if you are all okay. Sir has already come.
So, good morning to you all. I welcome you to this webinar on emerging materials for energy and environmental applications. I'll be giving a review of this workshop later on. But first and foremost, I would like to invite our director, Dr. Rakesh Kumar, to deliver his welcome address. Dr. Rakesh Kumar, please.
Good morning, Sadhna. It's actually a very pleasant, feeling for me that I've now sat with Professor Yadav after a long time. So welcome to Yadav for our seminar, who is a distinguished professor now at ICT. He doesn't need any introduction, but he just needs, all namaskaram that can be given to him for all the leadership quality that he has shown. And thank you for joining us this morning. Other colleagues who would be joining or may have joined, Professor Spas Kolev, who is from University of Melbourne, Professor A.K. Tyagi from BIRC, Professor Dipankar Sharma from Indian Institute of Science, Dr. A. Venugopal, of course my colleague Dr. Sadhna, and all the colleagues who have joined today. Just wanted to take a small journey back in NEERI. Although NEERI has been working in the environment-related materials for a long time, but this division which Sadhna heads, Environment Materials Division, came sometime 2000-2001. So it's almost like 19-20 years of journey with a very specific mandate of doing work in environmental materials in this institute. So while we have been doing something which is significant, of course there are more scope and more work that can be done. But some of the areas that we thought was very important, which we need to refocus, and all the experts who are joining today, they would probably guide everyone, and as well as they themselves can also put in their thought what needs to be done. In current times, we find that the application of this field in the field of energy and water can be given more focus, although there has been a lot of work going on, but we could possibly look at that, how do we do more what we have been doing. Some of the recent developments in other cases, for example, biodiversity, agriculture and forestry, what kind of smart devices, smart materials, sensors which can be used to track what is the progress. And why this is required is these are the areas where you don't normally go. It's something which changes over a period of time. It's not an instant variation which takes place, but it is something which is actually creating some kind of I would say spectrum changes in our society as well as in our climate, which needs more studies. And unless until we have time series data over a 5 years, 10 years period, we will actually find it very difficult to make a good interpretation. And I find that the materials in this field can possibly do wonders. We have already seen during pandemic times what kind of different materials which are for virus killing or surfaces or even from air I want to do something is coming up. Our institute also has been working in this area where we are looking at how do we purify indoor air so that we don't have impact not only due to COVID but even any other air pollutants which are coming up. So when I look at the scope of this area is so wide and I would say very impressive that whole of institute like NEERI or ICT would continue to work and still not be able to do it. But yes, when we start looking at some of the areas, I find that some of the devices, instruments, which is meant for environment and energy related activities can possibly be the major focus in the beginning. And as we go ahead, the knowledge is something which can be applied in any field, particularly in this domain. That will be very, very powerful. So, welcome again, Professor Yadav, and all the dignitaries who are joined and who are joining, and all the colleagues and all the listeners for this seminar. We are doing this online specifically for the reason that we want to reach out to more people. In person, of course, is much preferable, but sometimes in person in current times is not working out. But this platform also is very, very great, and we need to connect with more and more people as we go ahead. So I'll stop here, and thank you, Sadhna, for organizing this. Please go ahead with your program. Thank you.
Yeah, thank you so much. I'll be now giving an overview of this workshop. Respected Professor Yadav sir, Professor D.D. Sharma, our Director Dr. Rakesh Kumar, other distinguished speakers who will be joining, participants, delegates, and my colleagues, a very good morning to you all. Well, it's my privilege to introduce the theme of this webinar to such a distinguished and intellectually stimulating gathering. Well, I, on behalf of our team of CSIR-NEERI and entire fraternity of researchers and practitioners of material development in catalysis, would like to extend a very hearty welcome to all the distinguished speakers and delegates. Well, at this point, I shall take a couple of minutes to specially welcome and acknowledge the able guidance of our mentors, Professor Yadav and Professor D.D. Sharma, who, in spite of their extremely busy schedule, are attending this webinar to sensitize us with the importance of emerging energy and environmental materials. Now, coming back to the focus of this webinar, we all recognize the benefits of collaborations, interrelationships, and interactions beyond any boundaries to multiply our scientific strengths. So, this webinar has been organized in this context, which will provide a platform to students, academicians, researchers, and practitioners for interacting with national and international experts. Well, in this webinar series being launched today, we have two keynote lectures by eminent and exemplary speakers of international repute. We all know they are none other but Professor Yadav sir and Professor Sharma, who have graced our conferences and workshops several times in the past with thought-provoking and stimulating lectures and have been guiding us throughout. I accord a very, very special welcome to both of my mentors yet again. We also have invited lectures from Dr. Gopal from our sister lab, IICT, and Professor Kolev of University of Melbourne, a collaborator of Dr. Krupadam, who will be displaying the video clippings and excerpts of his lecture and also highlighting exemplary collaborating work going on with this university. In webinar series 2, which we are planning in February 2020, it will be focusing on solar energy materials in specific, wherein we shall have lectures from Dr. Shivram, Professor Ajay Vinu from Newcastle University, Dr. Tagi from BARC, and many more would be joining in the solar energy utilization program, which we have been carrying out several times in the past. Other than that, we also propose to carry out webinar series on other topics like CCVS, that's carbon capture, valorization and sequestration, environmental nanotechnology, valorization of waste, which we call it as value materials, and then, of course, lot of new developments like materials for pyrotechnic formulation, so on and so forth. Well, most importantly, in the forthcoming series, we'll be organizing virtual demonstrations and which we were previously carrying out as part of the workshop and the conferences. But now, with that possibility not being there for at least another 6 to 8 months, we'll be organizing virtual demonstrations of systems like solar hydrogen generation, which is in reasonably good stage at our institute. Then also we'll be demonstrating some work like green crackers, so on and so forth. Well, with strong commitments of exemplary speakers, which I've already mentioned, I feel that this webinar theme is a right step forward to facilitate mentoring possible collaborations and further strengthening ourselves by learning new developments and ideas related to energy and environmental materials, which needs to be taken forward. Professor Yadav, sir, with his extensive industrial experience in chemistry, catalysis, chemical engineering, and of course, sun-related, that is solar energy-related activities, shall sensitize us today with spectrum of technologies and their existing scenario in India. Professor Sharma, who's also our mentor for TAPSON program, with his research interest in the science of strongly correlated electron systems, primarily based on transition metal compounds and semiconductor nanocrystals, using a wide range of experimental as well as theoretical tools, will apprise us with a wonderful revolutionary material, which is, of course, organic, inorganic perovskites. For sure, every word and thought will be important to build our knowledge in the area of energy and environmental materials. I reiterate once again that we are extremely happy and feel blessed that we have with us today Professor Yadav and Professor D.D. Sharma to grace this occasion. Well, at this point, I would like to take a small break and mention that Professor Yadav served after an illustrious and impact-making career in the ICT since October 1986, and particularly as Vice Chancellor and R.T. Modi Distinguished Professor and Tata Chemicals Darbari State Distinguished Professor of Leadership and Innovation for past 10.5 years, retired. I don't like to use the word retired on 29 November 2019 because he is definitely not retired. Okay, he's still continuing, but better late than never. We were unable to do the felicitation at NEERI because of all this situation. We would like to felicitate our mentor, Professor Yadav, sir, today by virtually offering shawl and Srifal. I hope you can see it, sir. Yeah, we shall be posting it today and it will reach you. Okay.
Thank you so much, Sadhna. Oh, this is a virtual. Wonderful. Wonderful. Thank you so much. Thank you so much. Thank you.
So I'll be very shortly releasing a souvenir in the forthcoming series, which will include a lot of anecdotes and pictures which we have with us while you have been mentoring us throughout, sir. So thank you so much for being there with us. Professor Sharma, popularly known as DD, is a walking encyclopedia, as we all know, on information materials, navigator for all researchers working in the area of plasmonic science, nanomaterials, and nanotechnology. We are blessed to have you with us today on this occasion. I feel I should make a special mention and thank our director, Dr. Rakesh Kumar, for his dynamic leadership in steering the teams for hosting this seminar, which underlines his commitment to the theme of this webinar. I have pleasure in welcoming you all once again to this webinar and look forward to fruitful interaction, deliberations, and sharing with us your insights and opinions on the theme of this webinar. Let's all come together and work for a cleaner, greener, and sustainable environment by designing different energy and environmental materials. A warm welcome to you all once again, and thanks a lot for the patient listening. So now I request Dr. Kripadam to take over, who's the co-convener of this program, and will start with the lectures. Okay, so Dr. Kripadam, please. Yeah.
Thank you, madam. So it is my pleasure to carry on the program. And today we have Professor Yadav sir, and I am giving a brief biodata of Professor Yadav. Padma Shri Professor Ganapati D. Yadav is one of the topmost, highly prolific and accomplished engineer and scientist in India. He is internationally recognized by many prestigious and rare awards and as an academician, researcher, and innovator, including his seminal contribution to education, research, and innovation in the fields of green chemistry, green engineering, catalysis, chemical engineering, energy engineering, and many other fields, related fields. Past 10 years, he served as a founding vice chancellor and R.T. Modi Distinguished Professor and Tata Chemical Darbari Seth Distinguished Professor of Leadership and Innovation at Institute of Chemical Technology, Mumbai. He is currently holds the title of Emeritus Professor of Eminence at Josie Bose National Fellow in ICT. He served as an adjunct professor at many universities, and he received one of the highest civilian award, Padma Shri, in 2016 for his outstanding contribution in the field of science and technology by the Government of India. Professor Yadav is one of the number one in India in physical chemistry within a 0.2% world scientist. That means he is one of the topmost scientists related to physical chemistry, recently surveyed by the Stanford University, United States. So his academic contribution is enormous. The data which clearly represent that he has given away 101 doctoral and 122 master theses, which is the first record in ICT and for any engineering professor in India. So this is a very seminal contribution. And he has published more than 460 original research papers and 180 national and PCT patents, granted 74, 3 books, and he is having a H index of 60 and citations more than 13,000. So this clearly represents his academic and research excellence in the field of chemical engineering. And he is a fellow of 3 Indian National Academies and also fellow of the World Academy of Sciences. And he is also Indian National Academy of Engineers. He is a fellow of Indian National Academy of Engineers. And he is also FRSC, that is a fellow, Royal Society of Chemistry, London. And apart from that, he is having a member in many governmental bodies and organizations which are funding for different research activities in India and abroad. So currently, he is the chairman of DST National Expert Advisory Committee on Innovation and Incubation and Technology Expertise. So like this, he has the honor of addressing 3 convocations of renowned universities. He is fond of literature, ethology, and Sanskrit. And it is a privilege for us to know that he has written the ICT University song. And he has as many as 50 documentaries on YouTube. You can view whenever you find time. So this is a brief introduction about the Padma Shri Professor Ganapati Yadav. And it is really our honor to have Professor Yadav with us. So now I request Professor Yadav to deliver his inaugural address for this webinar series. So I welcome you, sir. Please deliver your lecture.
Yeah. Thank you, Dr. Krupadam. Thank you. I don't know this. I think something is happening. This is a wrong slide is being shown here. I don't know why. This is a problem with this software.
So my co-convener, Dr. Nagababu, has just informed that more than 300 people have already joined. Okay, so I'm very happy to share this with you all.
You know, I'll try to upload my uh, okay, so
Yes, sir.
you are seeing it, right? Thank you. Thank you. You know, there was little hiccup, you know, this particular Microsoft Teams, you know, it has a different mechanism. So thank you so much, Sadhna, for inviting me. Dr. Rakesh Kumar, Dr. Kupadam, Professor D.D. Sharma, and others. I'm very delighted to participate in this webinar. I think this is a series on emerging materials for energy and environmental applications. And so we know the value of materials. So I'm going to take you through some of these interesting slides. Today's is a new world, and the new trinity is change, challenge, and opportunity. So, and what challenge we face because of coronavirus, and we have to change the manner in which we interact and whatnot, and we have to change like the butterfly change their colors. But you know that the butterflies do not have pigments; these are nanostructures. So this is one example where we start with the nano materials. So at the same time, if you are constrained, you have to leave the place and go somewhere else. So but there are problems associated with that, and that is the risk of taking a challenge and going to a new place. So the fish can fall in between these two vessels, or it can safely land in the other vessel and may enjoy that swim. And also there are other challenges and risk in life, and you may fall between these two. So what happens in that case? In other words, we live in a volatile, uncertain, complex, and ambiguous world, and we need materials and energy in every form to survive and progress. Never have so many compelling technological problems have occupied the positions of prominence in our system of values. Every moment something happens unexpectedly, posing a new challenge, and that we see coronavirus change everything. The way we think, live, meet, behave, congregate, or rejoice. And that is what we are doing now. None of this was even imagined a year ago. Constantly on our minds is the fear of the unknown and the uncertain future in every human activity. An invisible virus has held the whole world to ransom with devastating effect. The mightiest of the rulers have been humbled, no matter what weapons and facilities they possess. So, what is the fallout of this COVID-19? The energy scenario across the globe has become topsy-turvy, and I'm going to talk about it. And before this, the price war between Saudi Arabia and Russia had already brought down the prices of the crude oil substantially low, and then Corona happened. And nobody imagined the crude oil price being negative, to be precise, on 10th of April. And slowly, it recovered to another low, something like $18. And the pundits predict that unless the crude oil price, the Brent crude oil price is about, $45 per barrel, the industry will not survive. Some of them say the best number is $60. Today, actually, it is 51.48 US dollars. So much so, the fracking industry, about which a lot of talk was going on during the presidential election and the debates in the United States, that business is affected very severely. In fact, 7 of the big companies cut down their, their budgets by 7.6 billion dollars. Of course, the U.S. Energy Information Administration had predicted by the fourth quarter of 2020. Now, if there is no vaccine or therapeutic, this business will be severely affected. Luckily, last week, this Pfizer and, just yesterday, the Moderna, vaccines are available. So I think things will come to normal, but not for next 5-6 months. And so this AI had predicted that the crude oil prices will increase to 32, then to 48, and now it was 54. Okay. And at the same time, that the world normally processes about 97.4 million barrels per day. And during COVID pandemic, around May, June, that number had got down to 86. So it had not gone down substantially lower, but it was affected. So I'm going to show you two, compare these two businesses. One is the crude oil business and another is the biomass business. So we can call them the crude oil refinery and the biorefinery. And in this particular case, deliberately I've circled the hydrogen participation in the refineries. You see, this hydrogen comes from steam reforming of natural gas. Okay? That is the source for this hydrogen. And so everywhere hydrogen is required. This is number one. And even in the case of biomass, you look at the biomass, whether your biofuel crops or industrial waste or municipal, waste containing carbon, the agricultural waste or other oil crops, everywhere hydrogen plays a very important role. Okay, then why are we not going for hydrogen economy? In fact, I've been talking about it for quite some time, working in this area of hydrogen generation for the last 16 years now, and we have got quite a few patents. So I will tell you what happens, what should be the new economy, world economy that I'm going to talk about. So the one important thing in that particular slide, which I just showed you, is that whether you have a crude oil, natural gas or coal, the fossil fuels, going through the refinery, or you have the biorefinery, the fate of that, the energy thing is ultimately that ends up as carbon dioxide. Okay, that is known. That means, really speaking, we are talking about carbon dioxide refinery. Okay. So one of the questions we should ask, because this is given as a solution everywhere across the world, and we analyze this and we published a very interesting paper which talks about the policies of the governments of the world, and that paper was published on the 21st September 2020. Till today, it has got more than 1,500 downloads, and we had so many people across the world, thinking on what we have said in that. And so we did some calculations. So one of the things we asked there, should biomass be wasted on making low volumes of biofuels, or should we convert biomass into chemicals and materials? And what happens in the year 2054, and this is the so-called, by 2050, we say that we will have net zero economy or net carbon zero economy. So we would analyze this. So you see that the energy consumption by fuels in BTU from 1980 to 2030, you see this is increasing from 1920. So you have some contribution of non-hydro renewables. Then we have also contribution of natural gas, but still, okay, coal and crude oil, they will be there. But by 2054, we will have exhausted all our crude supply. by using the current technologies. It does not mean, all crude oil will be exhausted, but new technologies will have to be developed. But this is the prediction, and predictions can go higher. So let us look at this particular slide. So, and on the today's modern society, which is so dependent on fuels, energy, materials, and basic needs, luxury, comfort, expectancy, life expectancy, and whatnot. We have simple feedstock like crude oil, petroleum. We take to the refinery, or you have natural gas and air and sulfur. Okay, these are our basic raw materials. And you go down this line and you can see benzene, toluene, xylene, what we call as BTX, and the butanes. These are our major feedstocks, okay? And then we go down and we have secondary chemicals, commodity chemicals, and then the intermediates, and then the final products which go into making of textiles or safe food supply, transportation, housing, recreation, communications, health and hygiene, name it. So what the public sees is only the finished products, okay? And they don't see what happens before that, okay? So the public has a very negative impression about the chemical and allied industry. They think that we can do without it. That's unfortunate it is, but that is the general impression. And when our government of India announced very recently that they will ban Chinese products, and you know that so many of these apps have been banned, and we know that. But banning app is very simple. Banning the materials which come into the country, whether they are intermediates or active pharmaceutical intermediates or something like that, which are dirt cheap, which are required for our industry, you cannot ban them immediately, but not many politicians will talk about it. So what does it mean? That means we can make them, and if we do not want to depend on China, so how do we make all these things? So, on a lighter note, I always ask people, because I mentioned that they have a negative impression about chemical and allied industry. I ask them, how did you begin your day today? And you look at the slide here, and I don't have to tell. And I'm sure all of you who are watching this, you have used your mobile phone. There will hardly be anybody who has not seen the mobile phone since morning. So that is how you begin your day. Okay, but we never ask this question. What are those, materials of construction or materials which are required for making this? So this question we ask ourselves. And the bigger question I asked, because this year, unfortunately, the Olympics was not held in Tokyo and it was postponed. But we know that in Olympics, many, many records are broken. In every Olympic, there is a record, new record. And when we say that, okay, that old record may not be broken, it is broken. Okay, like that Sergei Bubka going higher and higher, right? We know that. So what is the motto of this Olympic movement? Olympic movement has a certain motto, and that is CTS, ITS, and 40s, meaning thereby faster, higher, stronger. That means we are going to create new record. And when you look at this particular slide here, okay, look at this attire which these athletes are using. What are these materials? What sort of material which is used here? New materials, right? These are new materials. Okay, they don't perspire. Okay, they are lighter. They are not bulkier. They are not heavy. And I knew they are designed, so interesting. The aerodynamics is so that there is hardly any friction. That means this is actually adding to the speed of the athlete who is running this 100-meter sprint or 400-meter sprint or going in the swimming pool or the weightlifting, whatever. All this is because of the chemical and allied industry. Okay, so I would ask this question: name any products or various products used in Olympics or for that matter in your daily life. And think, you touch anything and you say, how are they made? Whatever you touch, wear, enjoy. Okay, are they synthetic materials? Are they plastics or polymers or composites or synthetic textiles or drugs or pharmaceuticals perfumes, rubbers, elastomers, name it, are the sensors and goggles and lubricants, whatnot, computers, whatever you use. How are they made? That is number one. And since we are living in a COVID era, can you show 3 man-made materials or products without the use of chemicals, including the mask which you are using? Okay. Or if you are sitting in the office, look at what chairs you are using, or the computers and the attire you use. Can you show that any of these products are made without use of chemicals? Okay, you have to scratch your head. And if you could show any 3, you will get a prize of 100 million pounds sterling, which has been waiting there from 2008. Answer is yes. Nothing can be made without chemicals. So the chemical and allied industry is a critical industry, and it is not an optional industry. Okay. This is very, very important, and this is what I'm going to talk about. So what does chemistry do? The modern chemistry is different from the old chemistry. The attributes that perhaps most distinguishes chemistry from the rest of the sciences is the ability of the chemist to control the structure of matter at the molecular level, from complex natural products like vancomycin to nanoparticles and whole genomes. In fact, the boundaries between biology and chemistry will disappear a long time. Biology cannot exist without chemistry, okay? And so that discovery should not remain in the laboratory itself. So chemical engineer job is to scale up these processes to make them profitable and eco-friendly. We understand that. So what change in chemistry which has taken place is that chemistry is increasingly shifting from structure to function. So what we are trying to do in today's new chemistry, that we are trying to bring many, many functionalities into the same molecule. Okay, it is not just one molecule. You add some more functional groups and say, okay, this will be giving color, and the other will give you perfume, or the other may act as something else. Okay, all sorts of things. That means we have to generate molecules or systems of molecules by using this new chemistry. And what it will do, it will give the desired physical, chemical, or biological properties. And that is what is required for today's world. Okay, these are our needs. So since this seminar of yours is on materials and energy and environment, let me give you some brief introduction to this. And I already mentioned that in 2054, we will not have any crude oil. Now, how are we going to survive? And at the same time, you remember the Paris Accord or the Paris Agreement of 2015, where nations of the world came together and they signed an accord. And they said that the temperature of the globe should not go beyond 2 degrees C during this century. And preferably, it should be 1.5 degrees C. How do we achieve this? Okay, so I'm going to discuss this. So one of these things which BP Energy Outlook in June 2020, they said this. So they gave this a very beautiful picture. And this is what I'm going to talk about. So what is, since 1980 till 2020, you see that now the CO2 emissions for energy use are something like 35 gigatons. Okay. And to bring down the temperature below 2 degrees by 2050, this has to be brought down substantially to about 10 gigatons. So that means 25 gigatons of carbon dioxide, which is going in the atmosphere, has to be contained. How do you do that? And preferably, to do that, so to bring it below this, if you bring to about some say 18, it will be 2 degrees. But if you want to bring it below 10 degrees, it will be 10 gigatons, it will be 1.5 degrees C. And that is what we are talking about, the net zero business, which the president-elect, Joe Biden also said in his speech. So in other words, in the share of the primary energy, the renewable share will increase. Now, these renewables means it would be solar, wind, geothermal, okay, and also the biomass. Okay, remember, these are there. And so, and we know that as the affluence of society increases, the electricity production also goes up. And that has to be based on net zero carbon emission. That is what we are talking about. So if you see this picture, if you see that the coal, which in 1900, we had maximum use of coal and which has come down substantially. But remember, by 2050, still there will be some coal, clean coal technology and all that. And countries like India will be using coal. So as we go by, we see that the natural gas, which is supposed to be even otherwise a clean source of energy, we say that natural gas, we will have new reserves to be found, and obviously this will go up. So let us look at, so the use of oil will come down. So in other words, we want to change the structure of the global energy system. And this is what happened because of the COVID. See, COVID has affected everything. The business is affected. So it is in the negative direction. Okay, it is in the negative direction. So the GDP has gone down. Typically GDP of the world is around 2-3%. But even you can see that. And by 2050, the oil demand should go down substantially. And that is what it is talking about. So if you look at the oil consumption, I already mentioned to you about 97.5 million barrels per day. Okay, that oil consumption will go down. Okay, and if there is a rapid transition, obviously it will go down. If it is by 97, it should go below 40. And ideally it should go below 20. Okay. So there will be a change in oil demand. And this oil demand is in passenger car, road, transport, and non-transport, like buildings consume a lot of energy. But people normally don't talk about buildings, but buildings also consume. And as far as the natural gas is concerned, you can see that natural gas, will you see the business as usual. And when there is a rapid transition, this will go down. In other words, the solar energy, wind energy, they will contribute substantially to the renewable resources of energy. So in the wind, natural gas is also viewed as a source of near zero carbon. Okay. And you have carbon capture and utilization and storage system. You can see that. So obviously, so we have the blue hydrogen, we have a direct energy. So by 2050, you can see that the natural gas will also be used for direct energy. So let us look at some of these things. And as far as, as far as this is concerned, the renewable energy sector is concerned, we see that we have geothermal and biomass, we have solar, and we have wind. And the solar contribution in net zero will be very high. And as we go by, we know that the cost of the wind and solar energy will substantially go down. What is today, it will go down by almost factor of 3. That is what we do. So the bioenergy and net zero, they are all linked. We know that. So we have biomethane, we have biomass, the other biofuels, hydrogen, and I'm going to spend some time on hydrogen energy, okay, and power, buildings, industry, transport. Everything is required. So as far as the wind and solar capacity is concerned, it will increase obviously, and it will go down, okay, that capacity, because ultimately it will reach a point of saturation. We can see that this is what is going to happen. And so this is, this is the scenario. And so the hydrogen, which I said I will talk about hydrogen. So we have gray hydrogen, we have blue hydrogen, and we have green hydrogen. So that hydrogen is coming, and of course it will also add to the power sector, the transport sector, buildings, and industry, and this will be required. And why hydrogen? So we are interested in the net carbon zero economy by 2050. Okay, we are and to make it net carbon zero, we have to look at carbon dioxide, which is emanated from different sources. Whether that carbon comes from renewable or non-renewable, it has to be converted. Okay, so this is another idea. So if we do that, our primary energy demand will increase. Okay, and if it is based on carbons, and it will happen. If it is less carbon, like hydrogen or solar or wind, the carbon dioxide emissions will go down. And that is what we want to do actually. So, and so in the case of renewable energy, you see that solar will have a big contribution, then wind. So more than 50% of the contribution by 2050 will come from these two sectors. Then, of course, we have hydro, then nuclear will contribute between 2.5 to 3%, and then gas, natural gas, and coal will be still used. Okay, mind you that coal will be still used. So no matter whether the carbon comes from fossil fuels or biofuels, there is a need to convert carbon dioxide into fuels, chemicals, and materials. And we have been doing work in this area in ICT in my lab. So based on our experience, we wrote this paper. So hydrogen is the cleanest fuel which can be produced from hydrocarbons like steam reforming or from water and can be used to convert carbon dioxide into useful products or treatment of biomass, whether it is waste or virgin, into hydrocarbons with the help of novel catalysts. And they can be novel materials, nano catalysts, and whatnot. We know hydrocarbons are reformed with hydrogen, but still we have to handle carbon monoxide and carbon dioxide. So this is where we look at of the carbon dioxide. Today, this number 410 is today's number, around that. So this is what, and if the carbon goes into the atmosphere, the carbon dioxide, okay, and if the percentage of the carbon dioxide goes to 2000 ppm, and that will happen business as usual, you will see that in the year 2200, okay, this will be 2000, and that will be disastrous. Why it will be disastrous? Because today we are talking about 2 degree or 1.5 degree by the year 2100, and when it happens it will be 6 degree or beyond that by 2200. So that means, and the coastal cities will sink, they will be submerged under water. So that means the climate change is a real issue and we have to deal with that. So how do we deal with that? So this is what we wrote in our paper. So we have carbon economy, that is fossil fuels, oil and natural gas. We'll still find some new oil reserves. So gas to liquid or crude to chemicals. Now refineries are talking, including Reliance. They say, okay, let us have a new business of crude to chemicals. In fact, the West Coast refinery, which was the IOCL and BPCL, HPCL that we're supposed to be in Ratnagiri, they also talked about variable fuel to petrochemicals ratio. So crude to chemicals. On the other hand, we have coal, and coal will last for another 200 years. So coal to gas or coal to liquid, clean coal technology. Okay, this is another. Or coal to methane or methanol. So you can see that on the contrary, you have renewable carbon. We can do chemical conversion or biochemical conversion or thermochemical conversion. See, in other words, we know that we can have direct chemical conversion of biomass. And one of the ways to do it, for example, hydrogenation, okay, fermentation or enzymatic conversion, biomass to gas or biomass to liquid. So whether it is a renewable or non-renewable, it ends up of CO2, which must be tackled to reduce global warming. So in other words, what we have, if we compare the so-called petroleum refinery versus biorefinery, both this carbon dioxide cycle is to be looked at. So valorization of carbon dioxide or the so-called carbon zero industry, we have to look at. So since energy and environment and climate change are all related, how do we do it? So, but before that, I want to tell you, so biomass or biorefinery is not a new concept. Many times people talk about green chemistry as if it is a new concept. No, it is not. The birth of chemical engineering, or for that matter, green chemistry is in the Solvay process, okay, 1865. So I have written a paper on that. So it is these were called the oileries. You know what? During 18th and 19th century, wells were captured. And these wells were used as a source of soap, oil, and whatnot. So what happened? As time went by, the population of wells went down, and there was a point of extinction of wells. So you see, these are the old pictures where the blubber of the well was used to make these things. So what we did, we analyzed the birth of this modern crude oil based industry. So this picture. So we have to thank Colonel Edwin Drake, who found this first oil well in Pennsylvania. in 1859. And so you see that from there on, this is the historical perspective. It is there in our paper. That paper you can download. I will give the reference also. So what happens? So you see that as we go along, what they used to do, there was you see, for example, there was a cracking, thermal cracking. And the gasoline or petrol, they used to dump in sea or in river because it had no use. What they used only was kerosene or, heavy oil and for making tar and all those things. So it was a kerosene produced by distillation, and that was used as an aluminum. Okay, and the other gasoline or petrol was dumped. This looks funny now, but that was the fact. And you go along, and around 1900, now this is where the Ford company came into picture. The Ford company found use for this petrol or the gasoline. Okay, and that is how Henry Ford introduces this, and this is where he used the petrol. And we go along in 1920s, the growth and demand of gasoline or the petrol increase, and that led to many, many different ideas, whether it is thermal cracking, then they introduced atmospheric distillation, vacuum distillation, and then they found lighter naphtha and gases and whatnot. And this was actually the birth of this petroleum industry, petrochemical industry. And so you go along, and during the World War II, actually, because of the superior technology, the catalytic cracking was responsible for the win of these Allied forces. Okay, the Allied ones were Nazis because of the superior quality of fuel. That is a historical fact. We are traced in our paper. Actually, you can see that means, yes, catalytic processes brought a lot of luxury and comfort to us, and also it led to the victory of these Allied forces in World War II. So you can see that in 1940s, there was a surge in production, and the refineries started becoming more complex and complex. And I showed you in the very beginning the use of hydrogen in refinery, whether it is hydrocracking, platforming, and name anything, how hydrogen has come to the rescue, and the same hydrogen is going to come to our rescue in biomass industry. Okay, that is what I'm trying to tell you. So then all these catalytic processes, catalytic polymerization, visc breaking, all those things started thereafter. In fact, the great Vladimir Ipativ, who was the Russian general, after his retirement, he literally ran away to the United States and he joined UOP. He could have been given a Nobel Prize for many of his catalytic discoveries and patents and whatnot, but he was not given because he was a military general. That is a history of technology. Very interesting. So we know that now the refineries are so complex that you don't understand, but the so-called atom economy is practiced by these refineries. And against this, we are comparing the biorefineries, and which are planned and developed across the world, and many data which we found from the US Department of Energy and other places. So look, these are the products, whether it is 1,3-propanediol, 1,4-butanediol, 3-hydroxypropionic acid, HMF is talked a lot, and you will find many people have written papers on HMF. Okay, we're starting with glucose and fructose and whatnot, and then you go to other, acids from this, linolenic acid, for instance, and all those things. You see, and you have succinic acid, you have vanillin, you have xylitol, all sorts of things. These are the products and feedstock for chemical industry. So what we did, we said if biomass is going to be a major source for fuels and chemicals, do we have the transportation lines? So we analyzed this information we collected, from the United States, okay, and we found a network. And so there is a word which is a terminology called as crack spread. What is the meaning of crack spread? Crack spread is making money over a barrel. So suppose barrel of oil is costing, say, $50. The crack spread should be at least $60, $70. Means that is the profit. By cracking, you get some crack spread. So what we found that if you take 1 kg of crude oil how many joules of 32 megajoules of fuels you can produce and 0.2 kg of chemicals. Okay. On the contrary, if you take 1 kg of biomass, okay, it will give us only 6 megajoule, but you can give us 0.8 kg chemicals. That means this is the title we gave to the subsection. Convert and not refine. Refining will not give you the value to your biomass. So the energy and mass balances on crude oil and biomass reveal to us that the biomass is better suited as a feedstock for making chemicals and not fuels. So biofuels is a bad idea, I'm telling you that. And this, many people will take objection to that, but I will tell you further what it means. So what we did, we took look at a typical refinery. So what is the conversion to chemicals or fuels? If you take 100% of biomass, I told you about the energy, only what we will get, it is only 10 barrels per second. And if you convert to chemicals, it will be 320 barrels per second. So you can imagine the value is more. And if in the crude oil, it is 215. So these are the figures which are based on the production capacities for, for petroleum refinery and biomass. Okay, that is what we did. So making chemicals from biomass is a better idea than burning it as a fuel. So in other words, bioethanol is a bad idea if you are burning it putting it in your petrol. No, bioethanol should be used for making ethylene and all other things. Okay, but not to be burned. So what do we? That is where the solar energy, wind energy, or other hydrogen energy will be very, very important. That is what I'm trying to tell you. So what we did, we looked at the US Department of Energy's data on biofuels. And we found that there are more companies, because, everywhere there is subsidy, there are more companies which are losing money on biofuels than they are making money. And the sizes of these bubbles here, they will tell you. So the failure is more here. You can see success is very low in comparison, and these are currently at pilot stage. These data we got from the US Department of Energy. So on the contrary, suppose you take petroleum derived products like vinyl acetate, butadiene, styrene, propylene, ethylene, bagasse. You see that the production of the selected petroleum-based, chemicals which are shown here, you see that, in this case, ethylene and propylene are the largest of these, coming from this. Oh, that means even otherwise, we want to make any further chemicals, these are going to be our feedstock. So why not make them for biomass, okay? So what we did, we also calculated the so-called thermal efficiency and the carbon efficiency, and there has to be a comparison. Okay, so we looked at the methane conversion processes like, our methane to olefins or methanol to olefins and oxidative coupling of methane or methanol. What we did was this. So in this, you see that hydrogen, this is steam reforming of ethane. So you see that the investment is about $500 million. Okay, the thermal efficiency is very high, but the carbon efficiency is poor. So here you go on this side, methanol, again steam reforming or oxidative coupling of ethylene, or the olefin. The size inside the bubbles in this figure represent the current capital cost. Okay, and the processing capacity, we took about something like 12,000 barrels per day. Okay, this is what refineries are typically. So we made calculations on that. And so we found that because one of the things our Niti Aayog is talking about is the methanol economy. Dr. Saraswat will talk about it. So we said, let us look at methanol economy also. So if you have the global production, so what can be made from methanol? This is the list of chemicals. I will not go into the details of that. But you see that methanol can also be blended with gasoline or petrol. Okay, we can do that. Yeah, but that methanol comes from where? We can get methanol from carbon dioxide also. So we looked at the so-called levelized cost of electricity, okay, which is generated by the combined cycle plants fueled by natural gas, biomass, and the natural gas. You can have conventional combined, combustion turbine, or you can have advanced combined. And the vertical line here is the break-even point, okay? And so this is the minimum and maximum cost, okay? And this is the break-even. So we found that this is a very interesting thing, that the biomass you see and the natural gas you see. So we see that this is very, very important. The levelized cost of electricity generated by this, combined cycle or advanced cycle, okay, is substantially lower than the power plants which consume either biomass or employ gas turbines. So this is what we found. So in other words, we talk about biorefineries. You take any biomass, we are talking about ethanol, diesel, methanol, hydrogen, and you go to chemicals. We say go for chemicals. Okay, don't go on this side. Okay, don't waste time there. So what it means, we can have a rich catalog of catalytic processes for producing a lot of value-added chemicals. So we looked at C5, C6, and you can see that I won't go into the details of this, but these are the normal chemicals which are used at feedstock. So including lignin. So we can play with lignin, because nowadays what happens, the lignin is burned, to generate power. But lignin can be used for many, many important chemicals. So your biomass, you pre-treat hemicellulose, cellulose, lignin, and you produce variety of these products, okay? Like xylitol, furfural, sorbitol, livininic acid, lactic acid, succinic acid, and 3-hydroxypropenic acid, ethanol, all those things. And we know that we can have direct product use or also derivatives, all those things. These are based on biomass, and we are saying they should be used as, feedstock for making chemicals and not. And in the case of carbon dioxide, all of you know that when you have carbon dioxide, you require some carbon dioxide capture, and then you have to convert that. So either you do the nature's way or you do it catalytic. So in other words, so carbon dioxide, photosynthesis, you get oxygenates, or you have treat with hydrogen and you get hydrocarbons and fuels. So methanol, dimethyl ether, and formic acid, by using carbon dioxide, and we have done substantial work in this area, they can be converted into this. And hydrocarbons. So in fact, very recently, somebody sent me a video that's somebody in Canada, I supposedly, they are making hydrocarbons for using carbon dioxide. So that is, so hydrogen is the key in all these things. So when you do this, so better catalytic materials are required for conversion of carbon-based feedstock. We also looked at waste minimization, process intensification, and of course renewable source of energy, and hydrogen as a source of energy and conversion of biomass into fuels and chemicals. So, and I will give you the numbers. Why? Because our economy is based on crude oil. And last year we imported crude oil worth 130 billion US dollars, which is 228.6 trillion tons. And our government wants to reduce the import. And that is why they are giving encouragement in renewable, solar, wind, hydro. And one of the pet theme of government is 2G ethanol. And right now we are saying, okay, we'll blend ethanol 15%, or maybe in future by 2022 over 22%, and we can blend it with, even diesel. So if you look at the India's global primary energy demand, this is going to be double to about 11% by 2040. And that is because of our population growth and also the prosperity of people. And so India will account for more than a quarter of the global primary demand between these two periods. And 42% of this will be met through coal. In other words, it means carbon dioxide emissions, and they will double by 2040. And we have signed that, a Paris Accord. So that means we have to take care of carbon dioxide, right? So gas production will also grow, but that will not keep pace with the demand which we need. Okay. And so actually the energy requirement by 2040 is 156% growth in Indian primary energy consumption, 11% share global energy in 2040, 58% of this will be in coal in India's power generation mix, and the growth in CO2, this will double, okay, by 2040. So at the same time, we look at the renewable energy sources. from about 20 million ton of oil equivalent to about 300 million ton oil equivalent by 2040. Okay, and we are talking about how many gigawatt. Okay, now we are saying 100 gigawatt, then 187 gigawatt, then 230 gigawatt, and whatnot. So despite this growth in renewables, coal will continue to dominate India's power sector. That means we need clean coal technology, right? So this is where we talk about carbon negative fuels or hydrogen as a source of energy. And I need not sing the praise of hydrogen. All of you know why hydrogen, okay? So yes, when you are hydrogen, you can have hydrogen vehicles, synthetic fuels, upgrading of oil and biomass, which is, and I already showed you in the very few slides about use of hydrogen by refineries and ammonia fertilizer, metal refining, other uses, heating. So hydrogen production and storage and our electricity generation, all those things are very important, right? So I already told you about this. So what we did, we developed a process. We have been working in this area from 2006. And the ONGC Energy Center is supporting my research. In fact, they have supported all my mega projects. And we produce hydrogen from water splitting, which is only about 95 cents. And the refineries use hydrogen where they produce it at about $2 per kg. And ours is 95. And I have not valorized the oxygen, which is going to be very, very valuable. Okay. So if you want to go for hydrogen economy, because that is the only way you can reduce the net carbon dioxide emissions into the atmosphere. So not only net zero, but we can recycle this carbon. Okay, so catalysis, water, and all that is water. So this is hydrogen production, no carbon, water is full stop. In fact, because of this, we also studied new age materials because we found that material of construction was very, very important in our hydrogen cycle. So we had to study something new. So anyway, I deviated and studied new materials and the hydrogen economy we talked about. So why hydrogen? This is well known. If you burn wood and go to hydrogen, the specific energy in kilojoule, per gram is the highest for hydrogen. Then methane, propane, oil, you go on this side, right? So hydrogen has the best specific energy. And there are various means of making hydrogen. So you have renewable resources, you have nuclear energy, or you have these fossil fuels. Okay. And somehow you make this hydrogen and then you store it and then utilize, right? So we did the analysis of the sources. So like natural gas, propane, biomass, coal, methane, you can see that this carbon-based fuels, so you need carbon sequestration, otherwise it is not useful. Or you have wind, solar, hydro, okay, or the uranium base, but there is a problem of nuclear waste there, and here is the problem of carbon sequestration. Anyway, hydrogen can be produced. So if you look at the hydrogen production technology, natural gas steep reforming constitutes about 95%, rest are others, okay, including the PM electrolyzers and alkaline hydrocarbons and whatnot. So even you can make this biohydrogen production through fermentation or biophotolysis. And if you look at the statistics, about 48% of this comes from steam reforming of natural gas, 30% from naphtha or oil, okay, 18% for coal gasification. These are carbon sources, right? Steam reforming of some carbon sources. Then you have water electrolysis and other sources. These other sources will be, for example, the production of, in the chlor-alkali industry. So no matter what you use, any fossil fuel, you require heat, and this heat can be provided by nuclear energy, okay, one of the things. And so you have hydrogen. So what we did in our case, so I'm going to tell you about that. The reforming technology, steam reforming, the most extensively used. Then you have autothermal reforming, and then you have partial oxidation. So in our case, we had studied two cycles. One is the sulfur iodine cycle, and another is the copper chlorine cycle. So there are other cycles like cerium chlorine, iron chlorine, vanadium chlorine, but this copper chlorine cycle is the one which we became highly successful, and we had many international patents in that. So this is the overall balance. So you see, Sadhna was talking about solar hydrogen also. When you have a carbon dioxide pool and you have biomass, you can convert that into the carbon monoxide, the syngas, and methanol and whatnot, and the hydrocarbon. So that is another thing. So if you look at the maturity of the technology, steam reforming and partial oxidation, they are commercial. Then you have the biogas gasification. Then you have the alkaline electrolyzer. Okay. So the efficiencies, they come down, but at the same time, they are commercial. So there are two methods now, the future technology where we have been working and the regular technologies, which are mature technologies, reforming, electrolysis, or the hydrogen which comes as a co-product. Okay, so this is what natural gas, steam reforming of the natural gas is the best used material. Then you have methanol, steam reforming, ethanol, you can have butanol, you can have ethylene glycol, you can have glycerol, all those things are there. Or the other coal gasification with carbon capture, and storage. So we worked in this area, okay, this particular area. And so we could collect a lot of data, like steam methanol reforming with carbon capture and the energy source is fossil fuel and the feedstock is natural gas. The capital cost for that plant is about $226 million and the hydrogen cost is 2.27. So the hydrogen cost, the refinery hydrogen cost, I told you already is about $2. So if you go down, there are some things which appear very attractive on this piece of paper. Okay. So we go down. Okay. So that means our number should be lower than this. So we have some 19 of this, which we analyze from the published data. And we found this is ICGOEC, this is ONGC Energy Center. They wanted their name to be attached to our process just because they're funders. So this is we call as. And so this has both solar and thermochemical and water splitting with copper chlorine. Our hydrogen comes as 95 cents, okay, per kg. That is the lowest. So this is very, very exciting for us. So, and what the Department of Energy is saying, US Department of Energy, that which small plants is about $4, it should come down to 3, less than 3, and it should be less than 2. Okay, that is what they are. The operation and maintenance is a little bit part of that, okay, plant. And you see the major cost in this is the electricity cost, and the capital cost is much lower. Okay, and here we want to reduce this capital cost. And so what is the long-term perspective of hydrogen economy? By 2030, hydrogen economy will be a reality across the world, okay? Because the electrolysis from renewables and nuclear will become very, very important. So in our plant, what we did in ICT's, my own lab, so we have solar energy, we have molten salt, we have also patents in that, and we have copper and chlorine cycle. We feed water here. We get hydrogen and oxygen, and that hydrogen, so we can, take to carbon dioxide and you can get syngas or syngas, or you can convert that into methane or hydrocarbons, or you can take oxygen, you can treat biomass. So actually what it means, so what we have, so one is this. So this is our technology, which is hydrogen production. This is another thing which we do, that carbon dioxide to methane and higher hydrocarbons. And this, so we are also working on this, that is methanol, hydrocarbon, dimethyl ether we have already done, and we are transferring this technology to one of the industries, formic acid, formate, syngas, you can imagine. So that means India's commitment to Paris Accord, we can make a huge difference, by contribution of this, our technology. So we are right now doing these pilot experiments with the help of ONGC, so 10 tons per annum to try to understand. We'll go to another stage. So, but this is very, very exciting. So why it is exciting? Now we say that I already told you that we have to bring down the carbon dioxide emissions, okay, to below this, okay, so below 10. We have to bring this down, okay? So that is what we see. So that is what our ideal goal. So ideal goal to contain climate change, and this is what we have been doing in our laboratory. So yes, so this is a very interesting aspect with. So while this, all of you know what is a linear economy and a circular economy, even in the circular economy, the plastic waste, hydrogen will play the biggest role, because I gave lectures on that separately. How hydrogen can be used to convert plastic waste into useful products and materials. So this is what it is. So in conclusion, the notion that biomass per se can replace oil as a feedstock for fuel and chemical manufacture was critically analyzed from economic and environmental viewpoints. Biomass is chemically and geographically incompatible with the existing refining and pipeline infrastructure in most of the regions, and these data we could get from North America, so it was easy for us. The biomass should be used for production of valuable chemicals and materials and not as a source of fuel, which is contrary to the belief what people have been writing and the books and so many papers are written, but this is what our analysis shows. So using crude oil for some time, biomass and shale gas to produce fuels, value-added chemicals, and commodity chemicals respectively will be the important part of this thing. So I think something happened. I don't know what happened, but anyway, that was okay. So so using methane as a feedstock for production of methanol also lays strong foundation for methanol economy. Hydrogen economy can be elegantly intertwined to make many chemicals from waste carbon sources, including biomass and C1 gases. And the government of India should adopt hydrogen economy to meet the demands of the Paris Agreement. That is the only way to meet the goal of that agreement. With this, I conclude, and I must thank ONGC Energy Center and this my JC Post Fellowship and others for helping me, and this is my group. Thank you very much. I think I took about an hour. I hope that was permissible. Thank you so much for listening to me very carefully. And if you have any questions, I'll be very happy to answer them. Thank you.
Thank you.
Yeah, Dr. Gopal.
Thank you, Professor Yadav. It's a very, very nice lecture, and it's very informative as well as impressive. And it will be useful to the listeners. The online, there are more than 400 listeners are there on the online. And of course, we can see many questions on online. So we cannot able to retrieve that, and we can pass on in future. So your lecture started with this hydrogen economy, and you concluded that hydrogen economy is the one of the most important alternative to reach the Paris Agreement. So, and it is a very, very impressive, and your statement, especially manipulation of properties of material by design of structures, is a very, very useful and important conclusion where people can take up this work for their future research. And your talk mainly focused on carbon emission reductions is very, very important, and look into the solar energy perspective. So, and your story about the how oil industry come up and how the sometime back gasoline is thrown out into the rivers is very, very attractive and impressive story. So we are really enjoy with this one. And the another statement, that is biofuel is a bad idea, but biomaterials, that is resources from biomass, is a very good idea. So this is definitely very interesting, and we also willing to take up this work. And you also introduced the new terms, which are very new to me, of course, like a crack spread for biorefinery and others. So really I enjoyed, and we enjoyed your lecture. And at the end, I have a couple of questions, so which I think it will be useful for other listeners on the online. The first one is how we can recover heat from the systems. Is there any application of new emerging materials such as nanomaterials or biomass-based materials which can be used to recover heat from the processes? Because heat recovery is one of the new area, or it may be existing long back, but it is neglected. So, sir, can you throw some light on how we can recover heat from the systems using new heat recovery?
Yeah. So, that is a part of the process system, because you have to design plant and machinery where you do heat pinching in the exothermic reactions. But if you are cracking something, it is an endothermic reaction, remember. Okay, cracking is an endothermic reaction. But in the other cases, wherever there is a exothermicity, we always can pinch heat, and this is heat pinching is very common process. Okay, so for example, I will tell you a nice story. That is, if you know FCC, fluid catalytic cracking, we use USY, the ultra stable Y zeolite as the catalyst. It's the best catalyst. Okay, that was designed over the years, and most of the refineries across the world use that catalyst. But remember, it gets deactivated within fraction of seconds, and it has to be regenerated. And so there is a regeneration stage. And how it is regenerated? It is regenerated by the burning of the carbon which is deposited on that catalyst. If you have a catalyst where there is zero carbon, then you can't do it. You require some catalyst to provide that heat for that. So it is. So if the catalyst is producing no carbon, that is not a good idea. You remember. So yes. The technology development teaches us many things. And this is one such thing. FCC is a very good example of engineering marvel, where you take the catalyst out and then recirculate it, you burn the carbon and bring it back. So this is very common, and refineries teach us many things. The most atom efficient processes are in the refineries.
Sir, the second one is which is related to application of nanomaterials for pollution control. Especially, we are facing a pandemic situation with this corona. So now many scientists are looking antibacterial, antiviral, and antimicrobial in overall. So how you can vision this area in future?
Yeah, it's a very good question. Perhaps traditionally three-way catalysts were the nano thing, right? The three-way catalyst which you have the exhaust of automobiles. Here, in the case of this pandemic, you have something where you want to, treat. For example, silver-based systems, as antioxidants and are the anti-pollutants. You know that silver is used in many places, okay, to give one control odor. So that is one important thing. Or even you have your clothing which is coated with nanoparticles, where you have the antibacterials or antimicrobials on that. That is being developed. In fact, one of the things for the mask which you are using, if it can self-regenerate, if the virus sits on that, it should be killed by that mass in situ. That is the whole idea. So obviously, a lot of work is going on. Very interesting work is going on. Even in India, a lot of people are doing it. But I know technology develops as a necessity. Necessity is the mother of invention. No, so this is what happens. Nobody would have imagined that in 9 months you will have a vaccine. It takes decades to develop a vaccine, but it was a necessity of the world. So are the sanitization business, hand sanitizer or this and that. Nobody has imagined a year ago that this business will be flourishing like anything. Of course, it affected some other businesses, but that is a business, right? So yes, I'm sure even in this pandemic, treatment of this PPEs, what you do with that? Okay, how do you treat it? How do you dispose them of? Whether you extract energy or some other chemical from that? That is another area which will have a relation with nanomaterials and nanocatalysts.
Sir, thank you very much for your very impressive and informative lecture, and we are very thankful and very happy to have an inaugural lecture by a person like Padma Shri Professor Ganapati Yadav. So thank you very much, and we are looking forward to associate with you and get guidance for our future research in this area of material science, energy, and other related fields. Thank you very much, sir. Thank you very much.
Thank you. Excuse me, I've got another meeting now, so thank you so much. Okay.
Thank you.
Okay. All the best to your conference.
Yeah, sure. Thank you so much for joining, sir. Thank you so much.
Thank you. Bye-bye.
Yes, Dr. Trupada. we'll go ahead with the program.
Yes, madam, we'll go with the program. And now I request Dr. Nagababu to go ahead with the program. As usual, as a formality to introduction to the speaker.
Thank you, sir.
And I want to say something here. Actually, the Professor Kolo is one of collaborators, and he has done a lot of work with us, especially in the field of carbon dioxide capture and development of a polymers, smart polymers for different environmental applications. So actually, in this series, I'm presenting our work, collaborative work, whereas the next series, Professor Kolo will be available for presentation. So now I request Dr. Nagababu to go for the formal introduction.
Thank you, sir. Good morning, ladies and gentlemen. Thank you all for finding time and participating today webinar. Myself, Dr. Nagababu, working as a senior scientist in CSIR-NEERI Nagpur. It is a great pleasure for me to introduce our next speaker, Dr. Redditota J. Krupadam. Dr. Krupadam completed his master's and doctoral from JNTU, Hyderabad. He done his postdoctoral from Dortmund University, Germany. He is currently working as a senior principal scientist at CSIR-NEERI, Nagpur. His area of research interest is molecularly imprinting polymers for sensing of environmental carcinogenic pollutants and pathogens, advanced materials for next generation environmental separation techniques, environmental applications, and the implication of nanomaterials, assessment and evaluation of environmental impacts of development projects, and graphene polymer nanocomposites for rapid destruction of recalcitrant pollutants. Dr. Krupadam has published around 60 international publications, 3 books, and he guided 5 PhD students and 41 postgraduate students. He is a visiting professor fellow at Case Western Reserve University, US, Louisiana State University, US, and University of Melbourne, Australia, and TU Darmstadt, Germany. Dr. Krupadam has received numerous major awards in recognition of his research. Number 1, National Award for Technology Development by Ministry of Chemical and Fertilizers in 2013, Fulbright Science Fellow in 2016, and Sir C.V. Raman Fellow in 2010. He received Outstanding Scientist Award for his excellent environmental science and engineering research in 2008 from CSIR-NEERI. Very recently, he selected for a Fellow Royal Society of Chemistry, London, called FRSC 2020. Ladies and gentlemen, please join me in welcoming Dr. Krupadam. Please, sir.
Thank you, Dr. Nagababu, for introducing me. So today, we are going to speak. I'm giving presentation on how emerging materials were used in different environmental applications. I taken the 3 important applications where most of the environmental science and engineering students and researchers can focus. That is water purification, gas capture, and the environmental metrology. So where we can use this.
इसको शेयर करना है ना, श्रेणी पे शेयर दिखाना, ये जो दिखा रहा है ओपन शेयर।
Yes, sir. It's coming now. Sir, unmute your mic.
Hello, able to see it?
Yes, yes. Carry on.
Good morning to all of you, and there is some link problem, so I'm giving my presentation now. So if you look into that, the emerging materials, how we can define, so how we can go for this, and how the materials are useful in different applications, that is water purification, gas capture, and environmental metrology. So at the NEERI is a national R&D laboratory, mainly works on inventing solutions for environmental problems. So if you look into that, and we closely work with the Millennium Goals and Sustainable Development Goals, which are declared by the United Nations. So if you look into that, there are 17 goals where this presentation relates to 3 goals, which are a clean water and affordable and clean energy and climate change. So I introduce the topic through the Sustainable Development Goals. And water is going to be one of the most demanding commodity in future, because even though the globe Earth is covered with a huge quantity of water, more than 90%, but the water which is usable form is very less quantity, is less than 1%. So if you look into the data from the United Nations, you can see that what is the different types of problems. That is, the availability of the water is one issue, and the second one is the quality of the water is another issue. So now the main challenge is how to make the non-usable water into usable water, or wastewater into a usable water. So this slide, actually I put it mainly to show the importance of water. And this is the areas where the water scarcity is available, and again this is the data from the United Nations. And if you come to the picture, so I already told you that the water purification would be one of the most important area of research, where many governments across the world, including the Indian government, has come up with a drinking water quality mission and other projects to provide a pure or drinking water to the rural population and the Indian public. So if you look into this picture, so this type of treatment is called as a advanced treatment, where the United States, they follow these type of treatment systems. But in India, we do not have such a system. We are having only 2-step process. One is the collection of the surface water, and then it will be sand filtered, and then it go to the disinfection before supplying to the public. So here the issue is, most of the drinking water does not meet the drinking water standards in India, especially the pathogens. So that is the reason India is one of the top countries where the children die with the microbial contamination of the water. So apart from that, Indian water, especially groundwaters, are enriched with the fluoride and arsenic in some part of the India. So that's why the treatment system, which is such an advanced treatment, we do not have, and it is expensive. The countries like us, we have to invent new simple methods. We can achieve the water quality for drinking purpose. So now if you look into that, nanomaterials or high surface area materials or certain different properties, this can be used in water purification. So if you look into this slide, where we given the nanomaterial, how they can work. They work as a coagulant, where they can precipitate out and settle down or float on the surface of the water, so that you can use that water. It can remove certain pollutant like heavy metals and even sometimes like a dissolved organic carbon and others. So that means nanomaterials can be act as a precipitation agent or coagulating agents. So the second one is the adsorption is a surface phenomena. Like activated carbon, we can use nanomaterials which have a surface area, high surface area to adsorb. That is a surface phenomena where it adsorbs and separated out. And the third one is oxidation, because the nanomaterials having a very good light and energy absorption capability where they can completely destroy the pollutant. So this is the oxidation. Maybe a photocatalytic systems are now coming up to address this type of treat certain pollutant. Like for example, if you treat water by chlorination, there is a possibility of forming haloethanes and halomethane. They are carcinogens. So that's why the dosage of chlorine during the treatment is important. So nowadays the people are using UV radiation and other systems. They are good enough to address such systems. So another very important area is antibacterial properties, antimicrobial properties. This is one of the most important and emerging area where this can address many of the pollution problems during water and wastewater treatment. So I mean to say that these nanomaterials having a very key role in water purification. And if you look into this, I given an example of how the coagulation process takes place, and we are using a traditional coagulant like alum, iron chloride, and lithium, lime, sodium hydroxide, and other things to precipitate and settle down. You can see at the bottom of the slide where you can remove the color and other things, and you can do it. So alternatively, there is another process nowadays. We are working on that light materials which can able to catch up the these pollutants, and they go to the top portion where we can remove easily the purified water. So this is one of the area we are working extensively on that, where we are developing nanomaterials and graphene based materials. And adsorption, I already described this method, which is adsorption is a surface phenomena, which is because of the unbalanced forces, energy forces, the material agglomerate or material sit on the surface of the material. So this is another area where we can use for pollution treatment. One of the most important adsorbent is the activated carbon, which is most widely used in water purification as well as drinking water purification and even industrial wastewater treatment. So this adsorbent is having some of the demerits, like the disposal of a spent carbon is one of the big issue. If you look into the interference of nano adsorbent, one of the most important advantages, it generates low volume of sludge. Whereas if you use the traditional adsorbent like the activated carbon and like the other geolytic materials and others, they produce a huge quantity of sludge. Whereas if you use the adsorbent, which are nanomaterials, the sludge generation is very, very less, and it can be easily settled down either by the gravitational force or it can be filtered off once they agglomerate. So this is one of the important area the people are looking. The advantage of nanomaterial usage is generation of the low sludge, which can be handled easily. And here I can say a few of the essential requirements the adsorbent should have. The adsorption is a surface phenomena, all of you know very well. So the adsorbent should have high adsorption capacity, and it should reach the equilibrium with a faster rate. That means the adsorption capacity should be high, and the kinetics should also be faster. So then what happens, the removal of pollutants or removal of metals, whatever it may be, the faster, so that it can accommodate more and more cycles. So that's why the adsorbent with the nano properties, that is a high surface area materials, is one of the desired property. And if you look into the carbon plant manufacturing others, so there is a method which is called as the hydrothermal method, which can convert raw material to carbon, and then it will be activated to generate channels and high surfaces which can accommodate more pollutants. So this is the way how the activation is done. So here I can show how the functionalization. That means sometimes what happens, these material, even though they are high surface, they could not able to take selectively the targeted ones. For example, you are having an adsorbent which is non-selective. It can absorb the gases like the carbon dioxide, nitrogen, and volatile organic carbons and other compounds. So actually, this makes that we cannot reuse the captured material. So with this AM, there is a concept of functionalization. That means you are fixing certain functionalities on the surface of the adsorbent so that it can selectively take up where you can reuse it. So one of the best example is if you want to use the adsorbed carbon. So there is a need to selectively uptake the carbon dioxide, and then you can make the other value added products. So that's why the functionalization is very important step where you can achieve a degree of selectivity. That means you can selectively uptake the material. So if you look into the another one, that is a last figure which clearly demonstrates how you can achieve the selectivity. So this is nothing but a molecular casting or molecular imprinting, where you can cast the molecule on the surface and then you remove it and create a surface which is highly selective. So such systems are very much essential in adsorbent. So whenever the adsorbent is selectively uptake, you can reuse the targeted molecule. At the same time, you can reuse the adsorbent. So whenever you reuse the adsorbent, the cost will go down and the material loss is spent material is very less. So with this, so we need this type of material. Overall, I mean to conclude that with this adsorbent should have a high surface area which can achieve faster equilibrium as well as the high absorption capacity. Functionalization will achieve the high selectivity where we can reuse both the adsorbent and adsorbate. And another one is the adsorption is a low energy process which can be reused. Adsorbent can be reused or regenerated very easily. And I'm giving one of a classical example which were prepared by using a iron impregnated graphene oxide, which can easily take up the copper from the solution. So this actually, if you look into this, we and at all they developed this nanocomposite, which is a graphene oxide based nanocomposite, which able to remove at very low concentration. Actually, another very important area in environmental science and engineering is addressing a very low concentration pollutant. The pollution concentration is even less than 0.01%. I can say that they are in the ppm level, that is ppm and ppt level, parts per million and parts per trillion level. So addressing or removing such a low concentrations is really a great challenge. So that's why there is another approach to make high surface area material with specific functionalities. Here, iron and nickel have an ability to selectively bind the arsenic so that it can be removed from water at very low concentration. Even we developed certain graphene based materials which are able to remove the color from the wastewaters, and we achieved 99.999% of color removal at a very faster kinetic, that is within 2 minutes. So here there is another area which is already a lot of research work is reported, and that is a carbon nanotubes, where carbon nanotubes decorated with ceria, which is nanoparticles, are efficient to remove the arsenic and chromium. In the similar way, our country is having a fluoride enrichment. We can find up to 40 ppm of fluoride in groundwater. So we essentially required nano materials or high surface area materials which can be easily binds to the fluoride so that they can be used in practical applications. So perchlorate is another very important carcinogen which is widely found in waters, Indian waters, lake waters. So they can be treated with polypyrols which have the ability to bind perchlorates. And fullerenes and multi-wall carbon nanotubes are very important materials for heavy metal enrichment. And also the hydrogen adsorption. One of the most important challenge in the case of hydrogen is the hydrogen capture and storage. So where we can use such a high material, high surface area material where we can capture the hydrogen and keep into the system and also using some of the application like fuel cells. The viral absorption, because of this current situation, the issue is the uptake of virus and filtering of viral particle from air and drinking water is a major challenge where the carbon nanotubes are already reported the application at a lab scale. The use of CNTs as a single molecule environmental sensors, because nowadays we are going into a level of a molecular level detection. So now these nanomaterials having a ability to work as a single molecule detection sensor. So these are some of the areas where we can use these adsorbents for different applications. Here I'm presenting one of the recent research work where we used a graphene as a knife, a nano knife, and put in a polymer surface which is having a cavities. So these polymers which is having a graphene not only kills the model the bacteria that is E. coli very rapidly. That means here we find that how this bacteria is killed and captured and killed by using this material. So we found that the graphene not only generate the reactive oxygen species, but also it generate heat at the temperature of 160 degrees. You can see the red mark which were scanned by using a thermal atomic microscope, where we can see certain areas, we can see the high temperature where graphene is located nearby. So this is one of the reasons where we can kill the bacteria very rapidly because of the localized heat effect apart from the generation of reactive oxygen species. So this study is recently reported in one of the journals. So these are some of the examples we can look into that, how we can use the high surface area or nanomaterials for different application. I already told that antimicrobial agents is another area where the people are working extensively on this area. So if you look into that, one of the important area even nowadays people are facing in water and wastewater treatment is formation of biofilms. And in other terms, the environmental engineers are very well aware of that. The bulking of the sludge. Once the sludge is formed, it bulks, and because of the high levels of high population or colonies of bacteria. So such bulking also prevents the purification capacity. So that's why this is an area where the surface coatings with antimicrobial properties would be one of the most important emerging area, where we can use some of the already reported by research papers where single wall nanocarbon nanotubes are very effective for activation of the inactivation of the bacteria. And the C60, the fullerenes are also widely used in the deactivation of the bacteria in water resources during treatment. So these are some of the applications where nanomaterial can be used because of their properties. And at the beginning, I told that how you can define the emerging materials. So now I came to the definition because of few examples where you can understand how we can consider the emerging materials, how we can define the emerging materials. As on date, there is no definition for this. So emerging materials are materials with improved properties. That means there is improved properties when compared to traditional ones to meet the high performance of the targeted application. So, and usage of low energy and materials during preparation. That means the emerging materials prepared with a sustainable consumption of materials as well as the energy. And they should be cost effective and environmental friendly. And during engineering, they should be durable. They cannot be one-time use materials or like that. They can be sustained for longer duration. So this is the some of the criteria which the emerging material should follow. So now look into that. These are the some of the examples of the emerging materials, that is nanometer scale materials, carbon-based material like carbon nanotubes, graphene, carbons, polymer and polymer nanocomposites, because they are cost effective and you can mold these material to achieve your targets. And the hybrid materials like MOFs, MOF is one of the fascinating field where which is having a very high surface area. You can go up to 6,000 meters square per gram. So which is more than 100 times higher than the most of the materials commonly used like activated carbon. And metal oxides and inorganic materials, this is another very important area where these metal oxides having a different energy spectrum and optical properties which can be used in the development of plasmonic materials where they can use as an effective photocatalyst. So we cannot neglect the natural materials because natural materials are natural given materials and they are environment friendly. And some of the natural materials which can be prepared from the biorefining process also. So these are some of the examples of high surface area, high energy materials which can be used. Let's start with the fullerenes C60, single wall nanocarbon, carbon nanotubes, multi-wall nanocarbon tubes, and silver nanoparticles. So here the silver nanoparticles nowadays, most of the water purifiers are designed to have silver nanoparticles where the silver nanoparticles having antimicrobial properties which can be used. So nowadays the research is going on and some laboratory scale demonstrations were also carried out by some of the research groups in India and abroad. And quantum dots, so quantum dots is you can see your televisions with a high quality because of the QDs which are used in the screen preparation. So but the QDs is one of the disadvantages, that is they are highly toxic materials. Mostly they contain the cadmium is one of the constituents. That's why we need to devise a better materials for these applications. And ND is a nano diamonds because it is not well explored area where mostly they are the cyclohexane related class of compounds. Mostly they are the adamantines. They are very stable cyclohexane type of structures. So they are having a very wide application, mostly in the case of optics. And geolites is one of the most important area which our department will work on that, and we are having a geolites with a different functionalized geolites where we can use the carbon capture. But the geolites are a very wonderful material for capturing of carbon dioxide at high temperature. So the limitation is the water content. If the water vapor is there, so the geolites will be spoiled. So another area is a polymers which is having a specific cavities which we can achieve the high surface area as well as also selectivity, and they are the cheap materials which can be used in a sensing application, environmental sensing application. So we have a few success. I will give few examples in coming slides. And metal organic frameworks is one of the most important area where I already told these very high surface area materials. But the issue is they are not reached a scale-up level. They are at the laboratory scale level. One of the most difficulty may be they are the amorphous material. They cannot withstand with certain conditions. So that's why they are not. And graphene, of course, is one of the wonder material where we can use the graphene the high surface area material and two-dimensional material are a few layered material which can be having a very good applications in environmental field, especially developing a antimicrobial materials. So if you look into this, this is one of the very good slide, which I like this slide, how we can correlate the nanomaterial properties with the different applications. So for example, you want to use this nanomaterial absorbent, the size is a matter, and surface area is a matter, and molecular specificity is a matter, and hydrophobicity is a matter. Like that, these properties should be considered when you are designing for different applications, like a microbial, antimicrobial agent, and sensor. So what properties should be considered? This is the bulk or individual properties. So this is a very good slide where whenever you are going to design certain materials, so you can keep these properties in your mind. So copper removal, which is already given an explanation, where the nano diamond is as a bulk material which is hydroxylated and then it is polymerized to make a fiber-like structures, and then this fibrous ball put into the colored solution, it removes the copper. So this is a very recent investigations reported for removal of copper. So nanofiltration, I already told that this is having a wide application, especially in desalination purpose. A lot of research is going on. So I can say that those who, young researchers who are looking for that, to make a more quantity of water, desalination is one of the important technique, where you can use a single layer or few layer graphene to permeate only a pure water through that. So this is another area, even we are also working on this area, how we can make a graphene inclusive membranes to make seawater into a drinking water. So this is related to photocatalysis. I am not going to give a more detail about this because of a time constraint. So if you look into that, overall, the water purification, where the nanomaterials are high surface area materials or emerging materials, is divided into three groups, because the water contain the organic pollutants, toxic metals, and sometimes wastewaters contain an oil pollutant. So oil and grease is one of the important parameter for the drinking water quality, which should be less than 10 ppm, 10 milligram per liter. So by looking into this, so these are the different types of pollutants and how it can be addressed is given. One is organic pollutant, we can completely degrade by the photocatalytic waste and Fanton's reagent and advanced oxidation process. So that is the one way we can decompose the organic pollutant. And another one is adsorption, because the materials, nanomaterials are having a high surface area where you can capture the toxic metals. And the oil and water separation is one of the most important area where recently the carbon sponges were developed. So this is another area where you can address the oil spills and other applications. So these are the overall how we can remove different types of material by using the nano structures and emerging materials. So this is about the water purification, and what are your desired properties? One is the material which you use should be eco-friendly material, like especially coagulants. We need to develop the organic chemicals which can use as a coagulant rather than using alum and iron and other materials which generate a toxic sludge. So that's why we can use a coagulant which are organic chemicals. Another one is the effect disinfection is one of the important area where most of the disinfection processes lead into a secondary pollutant. They are much more toxic than the primary one. So that's why we need a complete disinfection, which can be achieved by using the nanomaterial, especially photocatalysis is one of the area we can look into that. The separation is very, very important, because your material, if it is a hydrophobic, it is very easily separated from the bulk of the system so that it can be easily removed from the treatment. So effective adsorbents, they are the rapid capture of pollutant and reusable. I already explained the earlier slides where we can go for this. And photocatalytic material for rapid decomposition of recalcitrant. That means the recalcitrants are nothing but difficult to degradable chemicals. So they take that, in other words, they took a long time for the decomposition, maybe years, hundreds of years. So like a microplastic. So such cases we can develop some photocatalytic materials, those can address this. So these are some of the areas in water purification. And now look into the gas capture. This is a second application of the nanomaterials where we can use the capture of gas. Especially I given restricted my presentation only to the carbon dioxide capture, where the other gases are mainly we are concentrating on volatile organic compound, VOCs, and the hydrogen, and also the methane. So these are the other gases which we are working on that to separate them from the flue gases or from the gas reservoirs. So here I'm going to say already Professor Yadav has given a talk on the very beautiful talk on the carbon dioxide capture, but here the carbon dioxide is the most important greenhouse gas because of its residential period is very high and it is also abundant. All of you are knowing very well about the global warming, where the whatever the sunlight which is received by the earth emits the radiation and heat which cannot be reflected back into the atmosphere, create a warmer earth. So this is called as a global warming, where this is because of the presence of carbon dioxide, where the carbon dioxide takes the prevent the dissipation of heat energy. So that's why the carbon dioxide levels in the atmosphere, increases the global temperature. So that's why there is a need to control the carbon dioxide or mitigate the carbon dioxide emissions, either at the source by using the renewable energy like a hydrogen, or you can mitigate them by using the carbon capture technologies, carbon dioxide capture technologies. So another very important adverse effect of carbon dioxide in atmosphere is it dissolves in water to form a carbonic acid, where the ocean's pH is dropped from 8.21 to 8.1, which is leading to ocean acidification. So once the ocean acidifies, then the marine life is highly impacted, and some generations may go for extinction. Some of the species will go for extinction. So that's why to maintain the ecological balance, we need to control the carbon dioxide levels in the atmosphere. So there are some technologies where the emerging materials has to play a key role. So if you look into the atmospheric trend, where in 1958, where the Mauna Loa Volcanic Observatory, which is in Hawaii, in the United States, which is a reference location, where in 1958 the carbon dioxide levels were 315 ppm. So in 2019 we crossed the 400 ppm, and if this same trend goes as usual, so we can reach 900 ppm of the carbon dioxide concentration, which rise the temperature of globe by 5 to 7 degrees. So where the sustenance is extremely difficult. So you can see this actually how much carbon dioxide emits in tons and how the atmospheric concentration increases. This is a NOAA climate data which is received very recently, where we are already achieved 410 ppm of atmospheric concentration, and we are emitting around 35 tons of billions tons of carbon dioxide in 2020. So it is a very, the trend seems that there is a emergent requirement to develop certain technology to address the carbon dioxide emissions. So here there are few technologies we given a short review. One of the most important and commercially used technology is scrubbing of flue carbon dioxide into a amine solution. Monoethanol amine is the most widely used scrubbing solution which can be used to capture this. And based on this, about a couple of about 10 to 15 commercialized technologies, the slight variation in the conditions and solutions, scrubbing solutions were reported. So, however, the issues for this scrubbing, that is the absorption of CO2 into a solution, is having a few few constraints. The one is the regeneration of the spent solvent, which require very high energy. So that means, for example, the thermal power stations are producing 100 producing energy. For that, at least 30% will go for spent regeneration purpose. So that's why it's a very cost-effective affair. And the another one is the high quantity of absorber requirement. That is, absorbing solutions having a dissolution constraints. It cannot take more. So now it is a requirement to take up the absorber which can absorb more carbon dioxide than whatever you're now commercially using. And another one is, another very important drawback is the engineering perspective, where if you keep these scrubbing solutions, they are highly corrosive and they can stay no more than 2 years. We have to replace the equipment which is using for the scrubbing. So these issues are making the scrubbing is one of the, our absorption into this system is one of the a costly affair, as well as the not an environmentally friendly. So now it is a demand from a scientific community or industries that we need a anti-corrosive and low regenerating capacity solvents those have a high absorption capacity for the carbon dioxide. So, however, there is an issue of specificity, but these solutions are not much specific. So, there is a solubility of the sulfur dioxide which improves the acidic value much more. So, so these are these. If you look into that alternative, that solid absorption process, that means you are fixing the carbon dioxide on the surface of the materials is a low energy, and also you can make a cheap material. If you increase the surface area by creating the pores or micro porosity, it is possible to take up a high carbon dioxide content, which can be, where many research papers were reported that they can go up to 5 millimoles per gram at ambient conditions at 1 bar pressure. But if you go to the higher pressures, like where you go to a 20 bar and where you can achieve of up to 40 millimoles per gram, as a case for the metal organic frameworks. But it is not a, but such conditions are not really prevail in practical conditions. That's why we need to develop materials which can work at ambient conditions. So whereas in the case of limitations, if you look into that, where we have to do a lot of work on this, most of the adsorbents are low absorption capacity. And if you rise the temperature, because absorption is an exothermic process, where if you rise the temperature, then the absorption capacity decreases drastically. That means you can, at 0 degrees centigrade, the absorption capacity may be 2.5 millimoles per gram. If you go to the 30 degrees centigrade, it will come down to the 1.2 to 1.3 millimoles per gram. And if you go to the 80 degrees, actually we are looking at this temperature where the absorption capacity is 0.5 to 0.6 millimole per gram. So this is one of the limitations where we need to develop certain material which can absorb carbon dioxide at high temperatures. And another issue is non-selective, because we want to capture only carbon dioxide where we can reuse it and where it is easy to regenerate the absorbent. So such materials need to be explored a lot. And stability, because most of the adsorbents are spoiled by the presence of traces of water. So now we need to make a hydrophobic, highly porous materials which can be used for real life application, because most of the fossil fuel combustions not only emit the carbon dioxide but also give a water. So that is a real problem. So these are some of the limitations. So where we need adsorbents that are water resistive and highly stable for dry conditions. Because for example, geolites is a best example where they work very effectively at dry conditions, and traces of water will spoil the geolites absorption capacity. It comes out very drastically. So, and removal efficiencies are lower than the other technologies such as absorption. Absorption removal efficiencies are far better than the absorption. So, and the second one is, the last one is poor regeneration capacity, so that its reusability is an issue. So now these are the limitations where we can work and go further on this. If you look into the gas absorption systems, there are the three steps. One is a pre-treatment, which remove waters and particulates, and then it pass on through the column, absorption column packed with the materials, and then finally this is dissolved or dissolve the carbon, capture carbon dioxide in the third reactor. And all these reactors are performed coherently and continuously. So then these absorption systems are very effective. The key here is the pre-treatment, where you need to remove the water. And the second one is your absorption column should have a high performance material which can selectively capture. And desorption using the thermal or pressure swing methods are available, so we can use it. If you look into some of the materials which are polymer based adsorbents which are reported in the literature, so where you can create a high surface area polymers which are shown very promising area field, which starts from the melamine formaldehyde materials. Melamine is one of the wonderful material, I can say. That is one of the emerging material in the field of carbon capture, because it is having a highest nitrogen content in its molecule. So melamine functionalization of the resins is one of the most important area. People can work on that. Not only the polymer, the melamine formaldehyde carbons are also gaining attraction, because the melamine formaldehyde carbons contain high nitrogen content, which can be used for the carbon capture applications. So these are the different types of polymers which are reported in the literature, where you can achieve the highest absorption capacity of about 6 millimoles per gram. This is one of our study recently reported, how polymers can be created with the amino acids. Amino acids having a very great ability to uptake the carbon dioxide. That's why we functionalized the polymers by imprinting the amino acids, and then we captured the gases. So you can see in these figures, one, the B especially, is a carbon dioxide capture. The polymer which can achieve by around 2 millimoles per gram, which can be improved to about 6.5 millimoles per gram by functionalizing with the amino acids or imprinting with the amino acids. And these polymers are even practically stable up to a temperature of 60 degrees centigrade. And MOFs are, you can find a vast literature on the MOFs, how they capture the carbon dioxide. MOFs are decorated with the cations so that they can achieve the higher carbon dioxide capacity. And other thing, I'm giving one of the example here, where the carbon dioxide capture at higher pressures. You can see at a bar, 50 bar, it will go up to, it will go up to 500 centimeter per cube. It's a very, very high values you can. That means such pressurized systems, these will work very effective. The reason is, it is having a high surface area. At normal pressures, the carbon dioxide cannot penetrate into the matrix, where it can only attach on the surface. So now if you apply the pressure, the pores will be filled. Pore diffusion is one of the rate controlling step in this case. So in fact, such high pressures are not practically used at current situation. So the MOFs are another area where you can look into that, and especially the amorphous nature of MOFs is one of the important area where the researchers can work on. And I already told that geolite, these are one of the area we are working, and we recently developed a spherical geolytic structures which are called the cenospheres, which are light density materials which will float on the surface of the water. They have shown a tremendous CO2 capture capacity at high temperatures. So the geolites is another fascinating field, but geolites having a problem of spoiled the absorption capacity by the water. And now come to the what are the emerging CO2 capture materials? The waste-based materials. So fly ash and other materials derived from high temperature process, especially thermal power plants, can be molded into a carbon capture materials. And natural materials such as melamine, high nitrogen content materials, and some of the natural materials like carbonic anhydride mimics having a high potential in future. And graphene nanocomposite prepared from high carbon waste is another area. Recently, we prepared a carbon from a waste from sludge generated from the explosives. So this is, we are patenting now. It is not only removing the color within a few minutes, maybe within 2 minutes, but its capacity is extraordinary, very well compared to any other material report in the literature. So this is another area which is a fascinating area which we are looking for. And nanoparticles reduce the regeneration temperature of the solvent. Actually here, earlier I told that the high parasitic energy required for regeneration of the solvents maybe overcome by developing certain nanoparticles where at low temperature the carbon dioxide can be removed from this spent solvent and solvent can be reused. What I mean to say is, actually you need a high temperature to remove carbon dioxide from the solvent. That temperature can be reduced by adding a nanoparticle additives so that we can reduce the energy demand. Now we are using a 30% of parasitic energy. If you achieve the 5 to 10%, it will be good enough. And already commercialized systems can overcome this energy penalty by using a nanoparticles which can able to generate, which can regenerate the solvent at low temperature. So these are some of the emerging areas which carbon capture can be done. At the last part of my presentation, it's about 5 minutes. So the environmental methodology. So why this is important for us? Because all environmental pollutants are at ppm or ppt level, that is parts per billion or parts per million. So if it is a ppt, it is a 0.0001%. So to identifying or measuring the pollutant at such a concentration is extremely difficult. So that's why the interference of the materials, those who are having a high surface area or specific properties, are very essential in measurement science related to the environmental pollutants. So here there are the few areas we worked. One is dehumidifiers, and another area is chromatographic columns, where most of the chromatographic columns are non-specific, that generating a interference, and we can make a certified reference material, and it is a very good solid phase reaction material. And I already explained you that there is a single molecule detection sensor is possible. So here you can look into that. I'm giving you one of the classical example where certain nanomaterial, for example, polymers, which is having a imprinted site for a specific, can be used as a column material, which can take up only the selected DPA or selected any target. So these are these column. The column, we can see that chromatographic column is of capillary columns, which is filled with this type of material, which are high performance material. You can achieve the high sensitivity. In other words, it removes the interference during the investigation. Why you need to remove the interference is the environmental matrices. In environmental matrices are very complicated and more than 99.99%. So you want to monitor 0.001%, which is very, very difficult, where such type of a selective separations are very much essential. And this is one of our study where we monitored the refinery gases, and we able to track the polycyclic aromatic hydrocarbon, PAH, or polycyclic aromatic hydrocarbon. We were able to detect at 0.1 ppt levels by using a gas chromatography coupled with mass spectroscopy. So here you can see that how we created a polymer which pores, and then these pores were selectively take up only the targeted molecule, and these molecules were eluted when you pass through the gas chromatography. So this is another very important area where you need such materials. So nowadays, most of the people are using carbon-based columns or some polymer or resin-based columns, but they are non-selective, where environmental measurements require a selective material for separation and measurement of at low concentrated environmental pollutants. And this is another study which was recently reported, where we used an important tool in design of materials. That is a computational studies where we use the molecular simulation to identify how we make a design materials. Here we prepare a polymer which is specific to the dioxins. You may be knowing that dioxins are one of the important pollutants which comes from a different operations, like burning of plastics is one of the example, and pharmaceutical stacks which generate huge quantities of dioxins and furans, and each sample of analysis of dioxins furans is very expensive, maybe 20 to 30,000 rupees. So now we are planning to make a simple polymer strips can capture the dioxins and can be used directly in the GC where we can monitor that. And this is called, I can say that a single molecule sensors which we developed in collaboration with the American university, the Case Western University, where the gold surfaces were anchored with the terthiophene, and this terthiophene is having a ability to functionalize, and then we can take up the different types of molecules. You can see that there is a very clear evidence of existence of a force, which is the atomic force microscope micrograph, which can clearly demonstrate that. So this polymer was synthesized by using a electropolymerization method, where you can make a 10 nanometers to 500 nanometer thickness film on the crystal, the gold crystal, which can able to detect even a single molecule of the targeted compound. Here we use one of the PAH, that is a pyrene, which is one of the important air pollutant. So we used that and we demonstrated. And we also showed another application is virus sensing. That is this polythiophene, which were used for a virus sensing, where these cavities which are showed is specific to the virus. So we taken a rod-shaped virus and demonstrated this the application. And this is one of the sensors which we made it in collaboration with the industry. JetP is in Norway, which is a instrument manufacturing industry. They provided this the standard electrode. On that electrode, we prepared a thin film of 100 nanometers, which is having a implanted sites, which are pyrene, and then now you can detect 0.01 ppt. So such low concentrations are never reported. So we transferred this technology to this industry with a partnership. So another area which is, I can go through the two important areas from this, because I already told that low concentration of pollutants, the parts per billion and parts per trillion, is an important issue, where nowadays we are using only the carbon-based materials like activated carbon, other as a solid phase extraction materials. But we have to look into the different types of materials, where those can be reusable, like a multi-wall carbon nanotubes and single-wall carbon tubes. So the another important thing is the green chemistry-based approaches, where the waste can be regenerated and waste can be used for different applications. In another sense, The one industry waste can be used to the resource of the another industrial waste to generate eco-friendly materials and minimizing the environmental impact. I can say that this is called as a circular economy where you can use the material. That means whenever you are designing the materials, you have to design for benign. That means you have to think about not use the toxic material like a quantum dots. You are using a cadmium selenide, so you can remove those things and make for a environmental friendly material. Of course, carbon-based materials are one of the best materials, but they are having a reusability issue, so we have to overcome those things. And some of the challenges, which I already explained in other side, I am summing up here. Some of the R&D challenges are you need to develop the high surface area materials for CO2 capture, and also the material which can sustain at high temperature CO2 capture, and CO2 stable capture materials. And most of the studies were reported only to the lab scale, and field demonstrations are very, very low. So here I mean to say that whoever the researcher, they are doing most of the work at lab, but it should go to the land. So lab to land approaches should be followed. So whenever you are making a research effort, you have to think about how we can scale up and how can you apply for a field. This is a very, very important thing. I can say some of the examples, but due to lack of time, I could not go further into that. So if you look into the water purification, very important challenge is the disinfection using nanomaterials, which is a cost effective also. And water scarcity can be overcome by developing a membranes, and nanoporous membranes or graphene-based membranes. So desalinate water, which can be improve the water, drinking water availability more. More drinking water can get from by using this type of desalination. So oil water separator, this is not only the issue related to environment, it is also a process related. Industrial process are also facing this problem. So one of the solution would be the polymer nanocomposite, like a carbon sponges recently reported. They can address the oil spills in marine ecosystem, and also industrial separation, we can use these materials. So materials with plasmonic properties for rapid decomposition of recalcitrant. That means you can make the materials, especially metal oxides. Zinc oxide is one of these one, but the zinc is considered as a toxic pollutant. So we have to look into such aspects once you are designing high energy materials. Those can address the recalcitrant like pesticides and plastics and others. You can this is one of the emerging field where you need to develop material to address the recalcitrant. This one, dye removal is one of the pressing problem, especially common effluent treatment plants, where the dye removal is a big issue. So this is another area where you can target, the researchers can target on this. High absorption capacity, faster kinetic materials for heavy metals is also one of the removal. Again here, I mentioned the same point in the last slide, that is the field demonstration and scale up are a very, very important challenges. That means whatever you develop in lab cannot be restricted only to the lab, at least few things to go into the field. And the last slide is that the nanosensors for detection of pollutants at trace level is a challenge, and highly selective adsorbent for selective and trace detection as a solid phase extraction materials for pollutants is an important one. And the detectors, which are based on metal oxide nanoparticles, and one of the emerging area during our webinar introduction, our director Dr. Rakesh Kumar mentioned the monitoring of wildlife and biodiversity by using a smart sensor is one of the area where actually these are some of the solutions where we can develop a sensor or sensor arrays for the studying the biodiversity and tracking the path of wildlife. So high resolution gratings in spectroscopy is possible by using the nano diamonds. That is, now gratings are very important in spectroscopy. All analytical chemists are very much aware of this. So where you can use the nano diamond based gratings to get a high performance in selective splitting of rays. So that is a monochromatization. So such areas where the nanodiamonds have a major role. The materials with high stability, at temperatures are very much essential, like a atomic force microscope tips and other materials where you can develop the materials with high stability at temperature and pressure. So these are some of the challenges where you can focus our research. So overall, I mean to say that the emerging materials are materials which are fit for the purpose with a low energy consumption, cost effective and environment friendly. So whenever we are designing the material, we have to look into that, how the raw materials and the products are environmentally compatible. So, thank you for all of you for hearing this lecture, and I hope that if any couple of questions I can answer, otherwise you can write to me, we can discuss on this. So I am very thankful to all of you for patience hearing, and I am pleased to present some of my research work as well as the general issues related to emerging materials for application in energy and environmental fields. So that is about my presentation. Thank you for your patience here.
Yeah, thank you very much, sir, for a very informative and nice presentation in especially water technology and the greenhouse gas capture. And my simple question is, as you mentioned, the removal of, recently our sister laboratory CCMB has mentioned that there is a COVID-19 virus is there in drinking water as well as sewage water. So, as you mentioned, your material is removing the dye in 99.99%. So, have you checked that? Is there any antiviral activity of that material?
Dr. Nagababu is a nice question. The virus is having a different a target, I can say, because if you look into the color removal, color is we know well-defined structure, and they are a very small molecule when compared to the virus. So it is possible to remove the virus from this water, because we're already done few experiment on that. Due to lack of certain virus testing facilities, we are not went to the further on this. So the reason here, what I mean to say here is, we are already developed certain material for sensing applications, but we are looking forward to make adsorbents or certain high surface area material, those can capture the virus. So it is really possible, but we are not having a facilities for testing pathogenic virus.
Okay, sir. Okay. And one more question, sir. Last question. Can you suggest any good material for this microplastic degradation? Yes, is one of the big challenge.
The microplastics actually is a very big issue, because all plastics will go into microplastics, and there is a lot of reports on microplastic contamination in oceans, especially. The microplastics, once they are distributed in the water bodies, it is extremely difficult to treat them. So once you want to treat the water bodies, where your water treatment system, you can put as one of the unit operation, especially for photocatalytic systems, where microplastic can be remediated. The microplastics are not a defined chemicals. That is a big issue, and they are not having a defined sizes. So that is a big issue. So microplastic remediation is overall a different study, and even now there is no appropriate method for quantification of microplastic. That's why I'm little bit agitating to show something which is tell something which may not be practical. So that's why microplastics are not defined, and microplastics are not defined either by the structure or by the chemical. That's why it is not possible to treat them. But there is a way that photocatalysis is one of the solution for this. However, natural biodegradation is always there, so there is no issue for that.
Okay, sir. So over to the people. I think Gopal sir is there. I think ask some questions. Otherwise, other audience, Reddy is there, Fergie. I think no one have any questions, sir. So, a vote of thanks दे दीजिए उसके बाद. So next session will start around 2:30 with Dr. D.D. Sharma, Professor D.D. Sharma from IISc Bangalore. So vote of thanks is given by Dr. R.J. Gopal. Please, sir.
So again, you are hearing me. So the vote of thanks is a formal vote of thanks. So actually, this webinar series is a brainchild of our scientist and head, chief scientist and head, Dr. Sadhana Raidu. So during our divisional meetings, we decided to go for a webinar, which is not a single one, which is a series of lectures, series of webinars, so that all areas should be covered and it should be beneficial to the budding researchers as well as the scientists, where they can look into the emerging materials concept. So this is a brainchild of our head, and I am very thankful to Dr. Sadhana Raidu, who is instrumental to organize this webinar. And I'm very much thankful to our speaker, that is an inaugural address given by the one of the topmost scientists and engineer in India, that is Padma Shri Ganapati Yadav. So it is a great pleasure for us. Sir, we are very thankful for your inaugural lecture, and it's a very impressive as well as the informative, and we learn how hydrogen economy is coming in a big way in future. So I'm thankful to Padma Shri Professor Ganapati Yadav for giving the inaugural address. And I'm thankful to all the EMDNs, that is all scientists in the environmental materials division, especially Dr. Nagababu, who is associated with me from the beginning and beginning of the series, and helping in all the arrangements and others. So I'm very thankful to Dr. Nagababu, who is my colleague, and my colleagues, Engineer Wagmare, Shilpa Kumari, and Hipargi, and Hore, Suhasini Hore, and Reddy, and all our divisional project assistants, project fellows, and all other staff. So I'm thankful to all of them. And I'm also thankful to Professor D.D. Sharma, who is kindly consented to deliver a lecture in a very fascinating field, the perovskite-based materials for energy applications. So it will be the afternoon. So my vote of thanks is incomplete if I am not say about my director. So director sir is a very, very instrumental, and he is a guiding force from us from the beginning. And he always back to us and always encourage us. Sometimes he always pressurizes to conduct the webinar. So, sir, I am very, very thankful thankful to you, and especially you are given a very outstanding focus on materials which we can work out. Especially you told about the materials for energy and water treatment as a first one, where we are definitely will follow that. We are doing something, but as you desire, we make some technologies to go to the market. I know very well you are a person of technology development, and we definitely meet your expectations. And energy and water the materials useful for this addressing some of the problems. And you, in the second area, you throw light on smart devices and sensors for biodiversity studies. Yes, this is definitely one of the upcoming area where there is a lot of commercial value for this. We will go for this one. And the third one is, we already discussed about it, sir, that is related to antimicrobial materials. So to address the pandemic like situation. So we are already on the job to make these materials, and we could come up with the antimicrobial materials. And you, at last, you focused on the materials for indoor pollution. So indoor pollution is a very big issue. Yes, we can work on that. So at the outset, you were given a very good guidance and very good message to all of EMDNs and also the participant in this webinar, the areas where you can work. So I am very, very much thankful to you, sir. You given a very nice introductory remarks with such a very beautiful themes where we can work out. So this ends the formal vote of thanks. So now we are going to be a second session which will start as per the given in the schedule, that is around 4 o'clock, around 3:50.
Sir, Venugopal sir want to ask some question.
That's right.
Good morning, sir.
Nagababu, you mentioned 2:30. Afternoon session starts at 2:30, but Krupadam sir says 10 to 4, right?
Yes, sir. Yes, sir. I mean, students के लिए ऐसे बताया.
Okay. I'll see you there.
Yes, sir. Yes.
So actually, this meeting is going to be restart at 3:50 p.m.
Okay.
And this lecture will start with the D.D. Sharma, Professor D.D. Sharma, followed by our another speaker, Dr. Venugopal, who is your guest speaker. So I request all the participants to rejoin at around 3:30 to 3:50 so that we can have a second inaugural lecture followed by the lecture by the Dr. Venugopal. So this is about the coming next afternoon session. So here I declare that this session ends here. We meet again at 3:50. Thank you very much to all of you.
Thank you, sir. Thanks a lot.
As the program is sorted out, it is like that. So I will introduce you to the audience. We are having around 400 participants which are viewing your live, both on YouTube as well as the Facebook.
Okay.
And MS Teams, we are having a limited people of 6 to 7 who are organizers. So we are directly contacting with you. So the program is like that. I will read out and introduce you to the audience, and followed by any questions are there. A couple of questions can be handled, and then we move to the second lectures by this. And now, Dr.
You are muted. Sadhana, you are muted. We cannot hear you.
Yeah, I'm sorry for interrupting. Just 2 minutes. Yeah, actually, we have an RC going on. My lecture got postponed a little bit, and unfortunately, it coincided with this time. I'm truly sorry for that. My sincere most apologies. Okay, we have a research council meeting going on, and my lecture unfortunately coincided exactly with this time. I'm truly sorry about it. And yeah, please go ahead with the lecture. I'll join immediately. I have a lecture of just 20 minutes. I'll just finish off that and I'll come back.
Sure.
Okay. So thank you. Thank you so much for understanding and sorry.
See you later.
Yeah.
So now I am introducing Professor Deepankar Das Sharma. He's a popularly known as D.D. Sharma. Actually, he doesn't require any introduction, but as a formality, I will read out his biodata, which is he's given a very concise biodata. So Professor D.D. Sharma obtained a 5-degree integrated MSc degree in physics from Indian Institute of Technology, Kanpur in 1977, and a PhD degree in 1982 from Indian Institute of Science, Bangalore. He worked as Kernforschung Sangale, Zurich, Germany, as a visiting scientist during 1984 to 1986. Then he joined in as a faculty member in Indian Institute of Science, the Department of Solid State and Structural Chemistry Unit, and was the first holder of J.N. Tata Chair of IISc during 2017 and 2020. His research interest spans the science of strongly correlated electron systems, primarily based on transition metal compounds and semiconductor nanocrystals, using a wide range of experimental as well as theoretical tools. He has published about 480 scientific papers with more than 21,000 citations and H-index of 76 according to the Google Scholar database. He holds several patents. Professor Sharma is an elected fellow of all 3 science academies and engineering academy in India, and the third, the World Academy of Sciences, TWAS, and American Physical Society. He has received many national and international awards and recognition, including multiple honoris causa doctorate degrees. Professor Sharma had held a number of academic positions outside his parent institution, that is Indian Institute of Science, Bangalore, which includes the honorary guest and visiting professorships, such as Gaspard Mange visiting professor at Ecole Polytechnique, which is between May and July in 2019, very recently. University Professor of Computational Materials Physics, University of Vienna, May 2017. Guest Professor of Physics, Uppsala University in Sweden. And visiting Professor at Department of Complexity Science and Engineering, University of Tokyo, between 2001 and 2002. And Distinguished Scientist of CSIR, 2011 to 2016. MLS Chair Professor of IACS, 2006 to 2009. Adjunct Professor at TIFR, that is Tata Institute of Fundamental Science, Fundamental Research between 2003 to 2008 and also 2011 and 2014. And Honorary Professor of JNACR between 2003 and as on date. And SN Bose Institution, both the places, Professor Sharma is a honorary professor. And Distinguished Visiting Professor and Eminent Visiting Fellow at IACS, Kolkata. So this is a very brief introduction, and it is really our fortunate to have Professor Sharma with us to deliver a lecture. And today he is speaking on the organic and inorganic hybrid perovskites, a wonder material. So now I request Professor Sharma to deliver a lecture. So we are very happy to hear you, sir. Please.
Thank you, Professor Kripadam, for a very kind introduction and for this invitation, which makes it possible to come and participate, though virtually. I've been a regular visitor to CSIR-NEERI. I've also met you in my earlier visits. It's a very exciting place, and I do hope that in the near future, situation will improve so that we can again meet in person. Till such time, we have to take part in academic activities and exchange of ideas through this virtual medium. And so here I am. Let me start by sharing my screen. Please confirm that you can see my screen.
Yes, sir.
Okay, good. And also, please do not hesitate to interrupt me or to tell me that you can't hear, because sometimes the internet being unstable, you may not be able to hear me. Then you tell me so that I can repeat myself, because very often I can hear you, but you cannot hear me. Okay, let me get started. As I've promised, and Professor Kripadam just now said, I'm going to talk about this hybrid perovskites. We call them hybrid because it contains inorganic part as well as organic part. So it's not pure organic or pure inorganic. It's a hybrid material which has the structure of a perovskite structure. And I've given the name that it's a wonder material. And I'll try to tell you through a somewhat extensive introduction why we consider it to be a wonder material. Actually, it's a wonder material because it has some fantastic optically active properties. There are different kinds of optical activity that it shows. But for today's talk, I'm going to confine myself to one particular aspect of optical activity, which is related to the photovoltaic aspect of it. In terms of photovoltaic application, the particular class of materials that I'm going to talk about has really created revolutionary changes, and everybody's very active and very excited about developments in this field over the last 10 years or so. Before I get started, let me also point out all the research results that I'll be showing you from our own group have been very generously supported by ACRB, Nanomission, as well as DST, all under the Ministry of Science, Government of India, and also another arm of DST through international cooperation. They supported a new Indo-Austrian project, which also helped us to have some theoretical input from colleagues in Vienna. And also, over the last 3 years, we have been very generously supported by a private fund, Jamshedji Tata Trust, for our research. And I'm very happy to acknowledge the contribution from all these that made everything that you have done possible. The plan of the talk is going to be introduction, and I'm going to spend some time on the introduction so that you appreciate the field and appreciate why people are excited about it. Having told you about the introduction, that will naturally lead to identifying what are the open issues in this particular field, and the specific open issues are listed over here. I may skip this last one because I would bring in a slightly different topic here, but I'll explain each of these issues as we go along, and you don't have to try to remember them. So let's start with the introduction part. Let's see what we are plotting over here. It looks a very, very crowded curve, so don't worry about it. There are many colors, many symbols, and many things drawn over here. This is a collection of world's verified data on photovoltaic materials, photovoltaic cells, that is kept at National Research Energy Laboratory in Colorado. They maintain these standards and they tell us exactly how the efficiency, photovoltaic efficiency is increasing, which is plotted in the y-axis, with time, which is in the x-axis. And different color and symbol that you see here actually follows that a particular technology, because there are different technologies. The specific technology that is of importance or relevance is the silicon technology, and that is given the single crystal silicon technology is, you can follow this blue curve with solid symbols. That tells how the silicon technology with single crystal silicon has improved the photovoltaic efficiency with time. But more relevant for commercial application that you see all over the place, all the modules that you see on the rooftop, etc., is this polycrystalline silicon, and that's given by these open symbols, and then you can see that the efficiency has been steadily going up. Since it's a very crowded curve, let me surround this particular technology to give you a feel how the efficiency is increasing. This ellipse surrounds the silicon technology, and this major axis that I have drawn, which you can see is slightly inclined, is parallel to the average increase in the efficiency from year to year. So basically over this about 45 years, starting from 1975 all the way to 2020 end, it has been steadily increasing its efficiency, starting from somewhere in the range of 12% to ending up for the single crystal somewhere above 20%. This slow, steady increase has been critical in making silicon technology commercially viable. That is why you today have commercially all over the place photovoltaic as a viable source of energy generation, competing with the more classical fuel-based generation. And if there is another technology that is also popular and becoming more popular, which is called the thin film technology, which has a more rapid increase in the efficiency. And if I surround that with an ellipse, that shows this is the kind of efficiency increase that we have had over the years. Compared to that, with this wonder material that I'm talking about, and I'll compare that, and this is the ellipse that surrounds that particular technology, compared to the silicon technology back here, you can see that the silicon technology achieved an improvement over 45 years, more or less what this particular material has achieved in less than a decade. It is a fantastic increase in the efficiency that has now surpassed the efficiency of polycrystalline silicon in such a little short time at a rate that has been amazing. And that has got everybody excited. But not only the efficiency increase that is great, there are other things that are great about it. For example, silicon is not a good absorber of light. We know that. And that's why you need, the silicon modules have to be fairly thick such that the photons are collected properly, absorbed correctly. There have been competing technologies. One of the technology, dye-sensitized solar cell, aim to make the device thickness much smaller because that has great advantages. And it reduced the thickness down to a few tens of micron as shown over here. Then that improved to the solid state dye-sensitized solar cell technology that brought down the thickness of the device to about a couple of micron. And then came the extremely thin cells, absorber cell, which brought it down to almost to 1 micron thickness. And this technology that I'm talking about, based on this wonder material, the thickness of the cell can be less than a micron, half a micron or smaller. That's simply because this material is extraordinarily good absorber of light. So the efficiency is a net product of many, many properties. Absorption is one of the important property, and it has extraordinarily good absorption. So is this a new field? Actually, this field has had slightly longer than a decade history. And it is good to know about the history. It is in the beginning of 2000 that Professor Miyasaka, whose picture is over here, was researching these compounds, methyl ammonium lead iodide. You can see lead iodide part is the inorganic part, and there's methyl ammonium, which is the organic part, or methyl ammonium lead bromide for photovoltaic application. There was a reason why he was doing it, because this particular compound has a band gap which is ideally suited, nearly ideally suited for solar photovoltaic applications. But he could get efficiency very small, 2% or lower, and it was extremely unstable. And so most of his publications appeared in conference proceedings. The Parks group first pushed up this efficiency to about 6% in 2011. Still, the community did not take note of it. But in the following year, 2012, came two papers very close to each other that showed the efficiency to be 10% or more. And that sort of broke through the mental barrier of the community, and everybody in the photovoltaic community jumped up and started doing research on it. And in fact, thousands of groups all over the world got into this field to do research on various aspects of it. What makes it so good, this material? Let me point out, before I tell you that, let's know what the photovoltaic cell looks like, a solar cell. As I said, there's a material that's going to absorb photon. Once it absorbs a photon, it creates an electron and a hole. That electron and hole, you want it not to recombine inside the material, because then you will not get a current. You want it to drive a current in the outside circuit. That means you want to separate out electron and hole. You want to take electron to one side, hole to the other side. The way it is done is one creates a PN junction in this material such that there's a potential gradient, and electrons get attracted that way, holes get attracted this way. And once the electron and hole is separated, they drift, and the electron goes there, hole comes here, and then you can drive the current outside. So the properties needed for a good, efficient photovoltaic material is that it must be a good absorber of light. It must have this charge carrier that you create electron and hole. They must diffuse away from each other, so they must have long carrier diffusion lengths. And also a very slow rate of recombination. If they recombine, then I don't get current outside in the outside circuit. And the energy that I get is, of course, a product of the current multiplied by the voltage. Power, as you know, is the product of voltage into current. Current is the rate at which the photon is absorbed. So good absorber gives me high current. But I must make sure that I also have a high voltage, which is somehow connected to the band gap of this material. And there's an optimal value such that you can absorb a large part of the solar spectrum and yet deliver a high voltage. And that optimal value is in the order of 1.3, 1.4 electron volt. And so we need to have high open circuit voltage. That means the right kind of band gap of the material. This particular material, methyl ammonium lead iodide, is a very good absorber of light. It has a band gap, you can see, is about 1.55 electron volt, very close to the ideal band gap. It has an absorption coefficient which is absolutely fantastic, 10 to the power 3, 10 to the power 4 per centimeter. That's the reason why one can make very thin cell. It has a very long carrier diffusion length, hundreds of nanometers, and it has a high open circuit voltage of about 1.1 volt. So everything looks fantastic. Is that all? In fact, another thing that I didn't say is that it is also fantastic in terms of the fact that you can do solution processing of this material. Silicon technology, to make a silicon module, you have to input huge amount of energy. These are all high temperature processes. And then it will produce energy afterwards, but to create it, you have to input so much of energy that very often we are asking the question about the energy, auditing energy balance. These materials and these cells can be made from solutions so that temperatures that are involved, the energy input that is involved is very, very low. So solution processing makes it also extremely attractive for commercialization purposes. The work that I'm now going to talk about, which is from our group, addressing some of the open issues after I identify them for you, has been contributed by generations of members of our group, as well as contributed by my colleagues in collaboration with us, Professor Gururao, Professor Anshu Pandey, and their lab members. And these are the various generations of students, postdocs in my group, in our group. We also collaborate heavily with faculty members, my colleagues, Professor Sundaresh and Professor Narayan at CSIR, and their students and group members. And I mentioned that the Vienna group and the Italian group that we have interacted with. And the work that I'm going to present, some early part of it, is actually driven by this spectacular PhD student of mine, Dr. Sharda. She left the group since then to do a postdoc, and Dr. Bhushan Kore, who's now in Stockholm doing his second postdoc. And they published this series of papers during 2016 to 2018. And more recently, and Menno Bogdan, who is the person who drove the project, theoretical part of the project, and published these two papers. And more recently, Ashutosh Mohanty, who has just submitted his PhD thesis, did some very, very interesting, exciting work, one published and some unpublished work. And we have another collaboration with BRC, which was published just this month, earlier this month. And of course, I'm not going to cover all these papers. I'll take out some aspects and present to you so that I give you a feeling for why we are excited about this particular area, what the open questions are. To start with, let me tell you about the structure of this material. I told you it's a perovskite structure. A perovskite structure is very easy to visualize. Think of a cube, the way I have drawn a cube here. At the cube corners, put lead ions, and these edges of the cube, at the center of the edge, you put the halide ion, which can be iodine, bromine, or chlorine. And there is a position, at the body center position, a big void that can be filled up with some large entity. In this particular case, we have put methyl ammonium ion. That's what makes it hybrid. You can also put another organic moiety there, the formamidinium ion, or you can put a large inorganic unit like cesium ion. And all those compounds can be formed, and I'll show you some results from each of them. And that forms the structure. The basic electronic structure is supported by this lead iodide inorganic cage, and of this shown here. This stabilizes the structure, but also plays some very important roles, as I'll be explaining in the successive slides. Before that, let me point out that this methyl ammonium, we always abbreviate it as MA, calling this MAPBX3. X is one of the halides, which could be iodine, bromine, or chlorine. The first thing that I want you to realize is this methyl ammonium is an asymmetric molecule. It doesn't have a center of inversion, which means that it has a dipole moment. It turns out that it has actually a very large dipole moment. Now, a large dipole moment existing inside, if these dipole moments, all of them would line up parallel to each other, then we'll get a ferroelectric system. So the question, right from the beginning, people have been asking, do these organic dipoles make my system ferroelectric? In fact, Sharda asked a more fundamental question, not ferroelectric, whether this is polar, which is a question about the crystal structure. Does the crystal structure have centrosymmetric crystal structure or non-centrosymmetric? Why did she generalize the question? Because every ferroelectric material must be polar, but there can be polar materials that are not ferroelectric. So this is a more general question. In order to understand this, she of course looked at the crystal structure, but before I tell you about that, let me tell you why should anybody be interested in knowing whether it's polar or ferroelectric or not. I told you, typical photovoltaic cell, think of this as the space, this is the one terminal, that is the other terminal. I'm trying to get holes here and electrons there so that outside circuit I have current flowing. I have this PN junction at the center of the cell such that the top of the valence band looks like this, bottom of the conduction band looks like this. So if I create an electron and hole in this region, what would happen? The hole here would, for energy reason, go there because it can lower its energy. And the electron generated here will slide down this potential because it lowers its energy and come there. So automatically, this potential gradient separates out, pushing hole that side, electron this side. But imagine that the electron hole generation didn't take place there, that it took place here. If it took place here, you have an electron there and a hole there, neither of them feel the potential gradient strongly because the electron hole generation is far away from where you have created the p-n junction. In that case, there will be larger probability that this electron and hole will recombine with each other rather than the electron flowing down that way and hole coming this side and driving current outside. So that is one of the problem of this p-n junction-based solar cell. But on the other hand, if I have a ferroelectric material, if poled correctly, has a macroscopic electric field gradient inside by definition, which means it doesn't matter whether I create the electron hole pair here, here, or here, there's everywhere an electric field potential that would immediately drive the hole there and the electron there, and so the efficiency would be large. So there are many good reasons why one should like to have ferroelectric material serving as photovoltaic material. And that brings us to identifying the open issues. And as I said, one of the basic issues that one is asking, that this material, so good photovoltaic material, is it because ferroelectricity? That means we are asking the question, those dipoles on the EMEEA, how are they arranged? Are they ordered? If they're ordered ferroelectrically, then it will be ferroelectric. But if one dipole is pointing this way and the other dipole is pointing the other way, the two dipoles cancel each other, that would be called an anti-ferroelectric, and there will be no macroscopic polarization inside, and so that's not going to happen. So if it is ordered, we want to know if it is ferroelectric or anti-ferroelectric. And if it is not ordered, it can be either disordered statically or it could be disordered dynamically, like in a paraelectric state or in a glassy state where its dipoles are pointing randomly in different directions, but with time they are not changing. But here, that with time also every site is rotating and dipole is pointing in different way. So one would like to know all that. But before that, one would first like to know, is the crystal structure polar or not? Is centrosymmetric or non-centrosymmetric? It turns out that these questions, such fundamental basic issues, were not clear when we moved into the field. And we started asking this question first about the crystal structure. Is it a polar structure? Before I tell you that, I need to tell you about the phase transitions, because these materials show rich phase transition. MAPBI3, the specific example, and this is a DSC scan. As a function of temperature, wherever you see a jump, that tells you there is a crystallographic transformation across it. And it is very well characterized what we have. What we have in this temperature range, the room temperature and above, it's tetragonal. This is the relevant crystal structure for photovoltaic. The low temperature is an orthorhombic structure that we know is actually antiferroelectric. The dipoles are pointing opposite to each other. And then there is cubic. We are interested in knowing these ones. But also we want to know in all of them, is the crystal structure polar or non-polar? This is the report from the literature when we started working on it. You can see from 1987 to 2015, people have been looking at it. I told you there are three phases: orthorhombic phase, tetragonal phase, and cubic phase. For each of this is a low temperature for each of them. Without going into the detail of the space group symbols, all that you need to look at, if it is red with an asterisk, that means it's a polar space group. If it is black without asterisk, that means it's a non-polar centrosymmetric space group. And you can say for each of the phases, some people call it polar, some call it non-polar. Tetragonal phase, some call it non-polar, some call it polar. Cubic, some call it non-polar, some call it polar. We did single crystal X-ray diffraction, and our conclusion, of course, was that all three are actually non-polar centrosymmetric crystal structure. But there is a problem. These people are not fooled. The confusion is coming from a very fundamental point. The fundamental point is that whether it will be polar or non-polar, I say, it comes from the question that this is a non-symmetric, asymmetric molecule. Ma is methyl ammonium, CH3NH3. Now, CH doesn't scatter X-ray at all. C and N scatter but weakly. But since you have lead and iodine and they scatter so strongly that X-ray diffraction is not very sensitive to the orientation of Ma, and therefore sometimes there's confusion in the interpretation. So one can ask a question with different techniques. And that techniques we'll now look at that will not ask a crystallographic ordering, but directly address the behavior of the dipoles and ask whether it's ferroelectric or antiferroelectric. And if it is ferroelectric, I know what ferroelectric property is like. And this is shown for a well-known ferroelectric, lead zirconium titanate. And what I'm showing you is called the PE loop. You apply an electric field, the E, and measure the electric polarization of the material. Those of you who are not familiar with this, but familiar with the magnetism, this is exactly the BH loop. It is the applied magnetic field versus the magnetization developed by the material. And you can see at zero electric field, there is a remanent polarization, spontaneous polarization. That is a characteristic of ferroelectric. There's a large coercive field, and there's a saturation of the polarization. All this, given as this loop structure, is characterizes what a ferroelectric should look like. For example, yet another, barium titanate. You can see clearly the loop structure. We had looked at ourselves in some other context, some specific ferroelectric material published here, and that also you can see the polarization, the finite remanence polarization, large coercive field, a ferroelectric material. So now that we know what ferroelectric material should look like in a PE loop, I can go and look at the material MAPBI3. I'm looking at the low temperature 77 Kelvin phase, which I know is antiferroelectric. So the dipoles are pointing opposite, so there's no net dipole. So here the response is coming from the PBI3 cage, and you can see there is no loop, no PE loop like the ferroelectric. Slight loop opening coming from some lossiness, which is a technical aspect, but essentially the polarization plotted here is proportional to the electric field, and that's why it's a linear behavior. This is a typical paraelectric behavior. Now we can do this experiment for the room temperature, and what we see is essentially the same result as here, with a little more opening up of this gap, simply because it becomes more lossy, which says that this material is not ferroelectric at all. And then we can go and ask, okay, it's not ferroelectric, but the polar equation that we asked, the extra diffraction is not sensitive to carbon, nitrogen, and hydrogen. Let's look at it in a different way, and we'll be looking at it with second harmonic generation. What is second harmonic generation? If a material is non-centrosymmetric, that means polar, doesn't have to be ferroelectric, as long as it is polar, has optical activity, higher order optical activity, that, for example, if you come with sufficient number of photons with some wavelength, it interacts with this material, and the material combines two photons together to give you a higher frequency, double the frequency, half the wavelength photon. That is why it's called, this material generates second harmonic of the incoming wave. So the experiment is done, you push in some light, and look at whether twice the frequency light is coming out. If it does, that means it's optically active, second harmonic generation is happening, so it's a polar material. If you don't see any coming out of the higher frequency, double the frequency, that means it's a non-polar material. We did this experiment, and shown over here, we know that we are coming with about 1800 nanometers, so at 900 nanometer, we expect to see a peak, and this is from urea, which is a well-known polar material. You can see the peak in this case. Quartz, another material which is known to be polar, you can see the peak. The methyl ammonium lead iodide is giving you this one. This background comes from some other higher order processes, but you don't see any peak here. In fact, to look at this part more closely, the same plot is made here in logarithmic scale that emphasizes small changes. You can see that this is a smooth background through the sample. There's absolutely no peak where we expect a peak in this material. In fact, I can subtract out a smooth line to see if I have a tiny peak also. When I do that, what I see is shown over here. So it is this blue line with a smooth monotonic line subtracted out as the baseline, and this is the remnant noise. And we expect the peak to be here, and you can see there's absolutely no peak, no second harmonic generation, which tells you that the crystal structure is completely non-polar. Having established that question, that the dipoles are not ferroelectrically arranged, we would like to know what the dipoles are doing. Okay, before that, one quick thing that I would point out, a curious experiment that we did was that, these are the methyl ammonium. This black part with violet is the lead iodide inorganic cage, and the organic is this part, red and green, showing you that non-centrosymmetric. They are asymmetric. And this red and green is compensated by the next red and green by pointing in the other direction. That is in the ground state. But imagine that I bring in a photon and create an electron and hole. This electron will get attracted to the positive end, let's say the red end, and the hole will get attracted to the opposite end, the green end, which will make this dipole somewhat fixed or rigid, and then that by dipolar interaction can make the next dipole rigid. So in the excited state, because of electron hole generation, I may drive the system in a transiently polarized state. We wanted to know if that happens, because that also will have very important consequences. And that experiment we did is by bringing a high energy photon, creating the electron and hole, giving a time gap that we can control, and then coming with the long wavelength and looking for double the frequency, whether it's coming out. I'll only give you the answer that we didn't find. Okay, here is some of the results. Once again, here it's a cesium lead bromide where there is no dipole, so that I know in absence of dipole what happens. This is the signal from urea where we should get a huge signal, and it is the baseline where the signal from the material comes. So everywhere for different kind of delay, and you have down to 80 femtosecond delay to 2 nanoseconds. In this wide time window after the excitation, we have looked and we found absolutely no generation of this particular variety, which tells that this electron hole also does not cause any substantial transient polarization in the material. Okay, having understood that part, then one would like to know then what is going on with the dipole. If they're not ordering ferroelectrically, not making polarized, what are they doing? Now, as I've said, that can be actually studied very well by looking at the dielectric property, and I'll tell you a little bit about the dielectric properties now. Low temperature, I already said, is an antiferroelectric arrangement. We are more interested in the room temperature behavior, where we know it's centrosymmetric because second harmonic generation is inactive. But that's a time average description. What happens if I can look at it instantaneously? Do I see them polar? Do I see them rotating? These MA units could be rotating freely and independent of each other. Or they may be rotating very fast, but in a correlated manner. That means one and the other are rotating together in some way. Or they may not be rotating at all. They may be frozen, but pointing in different directions, so there is no net polarization, and it's in a glassy state. Can I find out which one it is? And that is where dielectric measurement that I'm showing you here, it is the real part of the dielectric constant shown for this compound MAPB-BR3 as a function of temperature. It's a complicated curve, so let me walk you through. There are many symbols that are for different frequencies. The fact that all different frequencies give me the same result tells me that it's not in a glassy state. Because if it is in a glassy state, it should become frequency dependent. But I'm interested in knowing what do the dipoles do. In order to know what the dipoles would do, I would first look at a material which doesn't have the dipole, which is the cesium compound. Cesium has no dipole, so I'll take out Ma and put completely cesium there. When I do that, my dielectric constant is here. More or less temperature and frequency independent down here. Very different from what I'm seeing in this part. This is a phase transition that happens. From the tetragonal phase, I get into the orthorhombic phase. In the orthorhombic phase, I know the dipoles don't contribute because they're antiferroelectrically ordered. So they couple to each other and cancel each other. And then you see that it looks much like the cesium case. As we expect, the cesium also has no dipole. And in this antiferroelectric state, there is no dipole contributing to the dielectric constant because they're all frozen, beautifully arranged, organized, and quite rigid in that sense. But this room temperature phase, we find that the dielectric constant, when the dipole is there, it behaves like this, is a 1/T dependence. And this must be coming from the dipole because cesium, which doesn't have the dipole, doesn't behave that way. So lead iodide, which is common to the cesium, is also here. So this additional behavior must come from the Ma. And this 1/T dependency can be theoretically shown comes from the dipoles rotating very fast. How fast they're rotating? I can say only up to the frequency that I've probed, which is 1 temperature points. Here I'm showing you a particular compound, again that 12.5%, 87.5% composition at one particular temperature, 250 Kelvin. And I want to focus on just this one single peak. This small region I have expanded here and showing you what happens when I change temperature. It's a very, very rich phase diagram showing many phase transition. At 310 Kelvin, you have one single peak, it's a cubic structure. Go down to 250 Kelvin, it splits into two parts, that's a tetragonal structure. You increase the temperature a little, this tetragonal splitting is vanishing, you can see, and a single peak is emerging, which is now complete at 120 Kelvin. It's again an orthorhombic structure. So just the same compound successively shows four different crystal structure: cubic, simple cubic, tetragonal, large cell cubic, and orthorhombic. And those structures are shown over here, showing what a complex, beautifully complex system of phase transition this particular composition, one composition can go through. And of course, you can make many, many compositions. So what I'm showing you here is the phase diagram in terms of the crystallographic phase. This is the EMEEA compound where formamidinium concentration is 0. This is the 40% formamidinium. Every dot is an individual experimental data point. So Ashutosh made composition at all these different points, varying the composition by very small amounts. And then each of those compositions, he took many, many X-ray diffraction at different temperatures to determine what the phases are, and then work out whether it's in tetragonal phase, orthorhombic phase, cubic phase, or large cell cubic phase. And you can see a beautiful phase diagram that emerges. The temperatures where mixed phase happens and most of the place. And you see that the stable compound that I said, when you put formamidinium with EMEEA, methyl ammonium, is largely the large cell cubic structure that it forms. But this is crystallography. Does this crystallography has anything to do with the physical property? And this question I'll illustrate to you, showing that beautifully the physical properties change in the crystal structure drastically. I've extracted not all the compositions, a few compositions. For example, this is formamidinium 5%, 10%, 15%. This is 17.5%, 20%, and 30%. And as a function of temperature, we are showing you the dielectric constant. Vertical red lines show you where the crystallographic transition takes place as determined for the phase diagram that I've shown you. It's a complicated one, so let me summarize it for you in a nice way so that you can follow it. Whenever we are in the tetragonal or the cubic stage, we see this 1/T dependency. That comes from the EMEEA ion rotating freely. But you see that as I'm going to more and more formamidinium composition, this gets suppressed and this temperature is moving up and this is becoming smaller and smaller. And here almost completely dominated by the large cell cubic. So I conclude when I'm in the cubic and tetragonal phase, there's a 1/T dependence because methyl ammonium ions can rotate freely. If I'm in the orthorhombic low temperature phase, I know that the EMEEA ions are forming dipoles in an antiferroelectric manner, so they don't contribute to the dielectric constant, and so the dielectric constant is more or less temperature independent, like shown over here. And that also we know orthorhombic nearly T independent. But for the phase composition, I find you see a strong frequency dependency. I had told you that when dielectric constant becomes frequency dependent, what it shows is that the dipoles are forming glassy state. And glassy state formation would imply that the dipoles are not able to rotate as freely before. And that large cell cubic then hinders the rotation of these dipoles. The way we try to understand this is that you see when the methyl ammonium is rotating, in order to rotate, the PBI3 cage also has to breathe with it because it has to accommodate the rotation. So once it's rotating, it's trying to breathe in a way that is in resonance with that rotation. And so if I have methyl ammonium in all the neighboring sites, they rotate in a coherent manner such that the breathing of this inorganic cage does not cost me high energy. But if I have methyl ammonium in one case and formamidinium in the other case, and formamidinium is also rotating, but its rotational behavior is very different from the methyl ammonium. And this is a result that I have not shown you, but this is what we published in the JPCL recently. And so the rotation requirement of the formamidinium is different from the rotational requirement of the methylammonium, and so they hinder each other, blocking each other, giving rise to this glossy state whose evidence is this frequency dependency that you're seeing. And that we believe is at the root of the stability that you are talking about. So the large cell cubic becomes glossy, giving rise to hindered rotation. So let me come to the end of my talk with 5 minutes to spare so that we can have some discussion at the end. So the conclusion for this part, other parts I have already concluded, that I have shown you this phase diagram. And this phase diagram beautifully divides itself, showing that the dipoles are dynamic and rotating here. Dipoles are glossy, frozen state here, and dipoles are in ordered state here, giving rise to very different physical properties, because of which this part, which is dominates and provides stability to these materials. And with that, let me end thanking you for your attention. Thank you very much.
Thank you, Professor Sharma. It's a very nice lecture, and you touch upon the two basics and relating the structure and certain properties which are very, very new to us, especially for me, where I'm not a physicist, I'm a chemist. So I can understand few of the things from your lecture. That is how the material inside the cage affects the outline structure, and how energy can be disseminated, and how the movement or rotation generate the different types of energy properties such as magnetism, light, and others. So as if you apply a photons, it can generate how we can make a material is a photovoltaic. So very, very nice lecture, sir, and I'm very thankful for you to be with us and give this beautiful lecture, because right now we are having access to very few people to interact with you, but maybe in a couple of days we can come out with the questions raised on online, YouTube and Facebook. So we'll definitely come back to you if we get a very good number of questions. So if anybody in the online can ask a question to Professor Sharma related to this. Maybe Dr. Reddy, you have worked a lot on photovoltaic and photosensors. So Reddy is on the line.
No, sir, he went for madam.
Okay.
RC, just now he went.
If any questions are there from any other people?
Not a problem. Otherwise, they can get in touch with me through emails, and we can discuss it later. That's not a problem.
So, sir, thank you very much, and I'm very thankful for you to be with us and guide us. And in future also, you are a very great source for us, resource as well as source in this field. And we are also starting some of the research work related to solar refinery concept, which is going to be coming a big way. So, where we need your guidance and your help.
I'll be very happy to be of use and value if I can contribute. I'll be very happy, because I know of NEERI's work. NEERI is an extraordinarily good place and doing extraordinarily well. I'm very proud of my CSIR background, and so I'll definitely be very happy to.
Thanks a lot, sir. Thanks a lot.
Thank you very much.
Thank you.
Thank you very much, sir, and we'll be in touch with you.
Sure.
And, it is a great pleasure for us to be with you, sir.
Thank you very much. Thanks a lot.
We'll go to the next lecture.
Unfortunately, I have to leave because I have another meeting. I'm very sorry. Today is a very bad day. I may not be able to stay on. If you would call me. Okay. I'll try to come back and join if I can.
We can understand. It is all right, sir. You are a very busy person. Still, we are fortunate that at least we have some time with you. We are having some time with you.
Dr. Reddy is there.
Sir,
Reddy, if you want to ask any questions. Yes.
Sharma sir, once again, madam told her apologies. She is tightly engaged with RC. She want to. Actually, your lecture is very, very, very nice basics, sir. Actually, in the metals and metal structure, ferromagnetic, anti-ferromagnetic, how they are cancelling and cancelling each other. Sir, once you kept that MEA and FA, another one, if we select the another one which having the low band gap energy axially connected to that one, which influence this tight rotation of the maximum cubic. That may nullify that and it makes the rotation like that. If I add another one more metal organic complex.
People are trying different. Yeah, people are trying many different combinations.
Yeah.
But the number of things that you can put at the inside are somewhat limited. Not too many things can be put there, but people are trying various combinations to increase the stability because it would be very important for practical applications.
Okay, sir. Okay. Thank you, sir. Thank you.
Thank you, Professor Sharma. Thank you very much. And
thank you very much. I take leave
looking forward you to meet with you,
sure.
sir.
Sure, I definitely will visit. Thank you.
Thank you, sir.
Thank you, sir.
All the best to you. Bye.
Thank you, sir.
Over to Dr. Nagababu. So the next speaker is Dr. A. Venugopal. So he's going to speak on the biorefineries and surface science and functionalities and binding sites. So now I request Dr. Nagababu to introduce our guest speaker, Dr. Venugopal from Indian Institute of Chemical Technology. Indian Institute of Chemical Technology, Hyderabad. So over to Dr. Nagababu.
Thank you, sir. Good evening, sir. Venugopal, sir.
Hi, Nagababu.
Yes, sir. Bonara, sir.
No. చెప్పండి.
Yeah. Good evening to all. It's a great pleasure for me to introduce our next speaker, Dr. Venugopal Akula. And Dr. Venugopal completed his master's from Kakatiya University and PhD from IICT Hyderabad and Usmania University. He is currently working as a senior principal scientist at CSIR IICT Hyderabad. His area of interest is catalysis and fine chemicals. He has over 100 publications and 13 patents, and he supervised 10 PhD students and 6 are presently working. He visited several countries such as Germany, South Africa, Australia, South Korea, USA, Brazil, and Russia on various research programs. Dr. Venugopal received Sistla Kameswari Siddhanti Young Scientist Award in 2009 and Professor Arvind Kumar Memorial Award in 2013. He is an executive member of Catalysis Society of India, a member in Indian Council of Chemicals, and also member in Indian Science Congress. Today he is speaking about biomass conversion process, understanding the surface active sites by probe adsorbed IR techniques. Ladies and gentlemen, please join me in welcoming Dr. Venugopal sir. Sir, please.
Thank you, Nagababu. Shall I share my slides now?
Yes, sir.
Can you please off the screen, Nagababu? I can't see my desktop.
Just upload the things, sir.
Yeah,
Yeah. All right.
How can I do it? Desktop window.
Ankush.
Nagababu.
Sir, my student is talking to you and he will guide you how to upload this one.
When I try to share my slides now, I could see your screen, not my desktop.
Yes, sir. 1 minute. Share the content. Share content of, I think we got some arrow mark.
Before the leave option.
So before the leave option, you talk.
No, there is no leave option here. Open share tree is there, na? I click here. The routine way I try to I could see desktop/window. I think I'm unable to see my desktop screen. Instead, it is showing your screen, Nagababu.
Sir.
Sir, Ashish. Sir, Ashish, you can do it, I think.
No. See, where is my presentation is on my desktop. No, I am unable to see my desktop.
You know how to upload, how to share. Okay, you can talk to me.
Okay, let me. I think I have to open my presentation and then I think I can be able to see my.
Yeah.
Sir, hello, sir.
Yeah.
Sir, please click the option on the right hand side, topmost right. There is a leave option. Before that, there is a upside arrow. Just click here, there.
రెడ్ కలర్ లీవ్ పక్కనే ఒకటి ఆరో మార్క్ ఉంటుంది చూడండి సార్.
ఎక్కడ బాది నాకు ఇక్కడ
మైక్రోసాఫ్ట్. ఓకే, ఆ పైకి ఉన్న ఆరో మార్క్ ని క్లిక్ చేయండి. క్లిక్ చేస్తే షేర్ కంటెంట్ అని వస్తుంది.
And then go to
share your screen అని వస్తుంది. Share your screen.
Yeah, screen your screen.
Yeah, right. Now
yeah, then go to presentation. Done. Excellent.
Okay.
Yes, we can able to see presentation. We can able to see the presentation. Yes.
Good afternoon, everybody. At the outset, I would like to thank Dr. Gopal for inviting me to deliver a talk on biomass conversion processes. In fact, the title is on materials, energy, and environmental applications. I thought of talking on hydrogen production technologies. However, Professor G.D. Yadav has given a nice lecture this morning. Then I changed my topic to some of the recent works that we have done for the last 5 years on biomass conversion process. What we have done is that we try to establish kind of operando IR spectroscopy using in situ IR kind of Harrick cell. So my talk will be on 2 different examples. The reason why I have chosen 2 different examples is that these 2 examples, one is alkyl pyrazine synthesis from crude glycerol, and the other one is gamma valrolactone synthesis from levulinic acid. These 2 projects we have taken up under CSIR-NEERI program as well as under 12th 5-year plan. My talk will be, the outline of my presentation will be on, I'll give you brief introduction on background on the bioglycerol and levulinic acid and the role of acid-base sites, how they could affect the catalytic activity as well as the role of acid-base sites on the product distribution, which we try to rationalize using different probe molecules with probe adsorbed IR studies. Apart from this, what we also have done, we have made a large extent of characterization techniques with which we could understand the bulk and surface properties of these catalysts, which is very essential while you are evaluating different catalyst systems for a given reaction X to Y. And finally, the catalyst poisoning studies by pyridine and 2,6-dimethyl pyridine as probe molecules. For example, if you look at the crude glycerol conversion, we all know that the biodiesel came into light about 30 years ago, and there were many plants were erected around the world, and people started producing biodiesel. As a result, what we get is a byproduct, that is glycerol. Glycerol is a commodity chemical, a fine chemical, but the problem is that this contains 90% of water and traces of some unconverted methanol and some amounts of catalysts like potassium hydroxide, sodium hydroxide, and the range of glycerol which is obtained as a byproduct will be in 10 to 28%, which means that when you are making 1000 kilograms of biodiesel, there will be 100 kilograms of glycerol in water. So under NIMCLI program, we were given, project to work on convert this crude glycerol into 1,2-propanediol and 1,3-propanediol, which we have completed this sometime in 2010. Then that was the time when CSIR was so keen to work on, development of processes, and it was advised by the then Director General not to publish any work which we generate data on conversion of crude glycerol to propanediols, because these are all, fine chemicals and highly useful chemicals. Then we thought, even someone is working in the project or a JRF, what should we do with the data which is not supposed to be published? Then we thought in a different way to work on what you call synthesis of alkyl pyrazines. For example, if you look at the top of the scheme, wherein ethylene diamine when reacts with 1,2-propanediol here over a catalyst system, that is a palladium modified zinc chromate catalyst, what is known as Lewis-Forney catalyst, this will form 2-methyl pyrazine. This 2-methyl pyrazine is an intermediate compound to make the anti-TB drug, that is pyrazinamide. So then I was just anticipating, if the reaction proceeds in a similar way using glycerol instead of 1,2-propanediol, I should expect this molecule. This is alcohol. Instead, what we have got is that when we subject these two molecules, ethylene diamine and glycerol, over a combination of zinc oxide and zinc chromate, we have got around 72% of 2-methyl pyrazine and 10 to 15% of pyrazinized products. Then we were in confusion how, instead of if the mechanism proceeds in this direction, we should get at least 50% of 2-methyl pyrazine, otherwise 50% of pyrazinyl methanol. But we could not get it. Then when we analyze the product distribution, and based on the different characterization techniques, based on the mass spectroscopy data and NMR data, clubbing all the different techniques, we have proposed a mechanism. What will happen is that when glycerol reacts with ethylene diamine, this will undergo cyclocondensation to form this particular saturated molecule. This will further undergo dehydrogenation to form pyrazinyl methanol. In fact, the reaction must be stopped here. If the reaction proceeds like a Lewis-Forney catalyst works for ethylene diamine and 1,2-propanediol. On the other hand, what we were getting is that large amount of methyl pyrazine. Then what we thought was that since zinc oxide, zinc chromate also contains some kind of acidic and basic sites, we thought that it is further undergoing dehydration to form a cyclic transition state, 2 moles of this forming 2-methyl pyrazine along with some aldehyde. If this is the case, we should at least expect a large portion of aldehyde. But large portion of aldehyde is not obtained during the course of the reaction. It was found to be less than 5%. So then there is a in situ hydrogen that is in situ formed during the conversion step 1 to 2. This hydrogen probably hydrogenating the very soft aldehyde group to form again this alcohol, and it is going in a cyclic manner. As a result, we are getting higher amount of particular 2-methyl pyrazine. Then the formation of pyrazine was expected from the what you call intermolecular cyclization of ethylene diamine. That is, 2 moles of ethylene diamine will give you a pyrazine molecule. This is a surface mechanism wherein I just want to show you the role of acid-base sites which are in adjacent sites that are acting or involved in the reaction. As a result, you are getting this particular product distribution. It is not so easy to understand the product distribution, especially when you are working with for cyclization reactions, because presence of chromium oxide in this particular spinel compound. Chromium has got a typical behavior wherein this particular molecule will further disproportionate to form dimethyl pyrazines and all. So anyway, that's a different story. So then subsequently what we have done is that when I try to use glycerol with 1,2-propane-diamine, we were getting 60 to 90% 2,6-dimethyl-pyrazine and 5 to 35% of some alcohol, 6-HME. This is 6-hydroxymethyl pyrazine. The product distribution was based on the catalyst that you could test with. So a higher amount of 2,6-dimethyl-pyrazine was obtained, and the use of this particular molecule is that this can be largely used in agro industry as well as a food flavoring agent. So these are the experimental conditions that we have adopted to understand the surface properties of these catalyst systems, especially. So then I'm going to talk on today. Initially, what we have done is that we have tested different metal chromides instead of zinc chromide. We have tried with the copper, chromite, zinc chromide, cobalt, nickel, magnesium, and iron. Initially, what we have done is that we tested this reaction using single component, that is glycerol. When we subjected glycerol alone over these catalyst systems, since this catalyst system, these metal chromides consists of some kind of acid sites and basic sites, you can see that when this glycerol undergoes dehydration, you will get a what you call hydroxyacetone. If this molecule undergoes dehydrogenation, you will get dihydroxyacetone. See the product distribution here. And the amount of hydroxyacetone was found to be higher over copper chromide catalyst, and the rest of the catalyst showed inferior activity. Similarly, what we have done is that using 1,2-propane-diamine, when we subjected this particular molecule over these catalyst systems, still copper chromide was working well with this molecule, and that was producing 2,6-dimethyl-pyrazine as a product. This goes by intermolecular cyclization using 2 moles of ammonia. But on the other hand, when you subject the mixture of 1,2-propane-diamine along with the glycerol, this reaction proceeds in a different way, wherein we are getting 2,6-dimethyl-pyrazine and some amount of alcohol. When we subjected all these catalysts to the mixture of the 2 components, what we could see is that you can see that a higher ratio of 2,6-dimethyl pyrazine over copper chromide catalyst that consists of copper oxide and copper. Please remember that these precursors were made in the form of hydrotolcite structures, just to have a uniform structure, uniform what you call layer structures. So then subsequently what we have done is that we have done varied ratios of copper to chromium. The top one is pure copper oxide, and then copper 3, CR1, 2, 1, 1, 1, 1, 2, 1, 3, and last one is chromium oxide. Now all these catalysts were characterized by XRD, and the crystallized size of the corresponding copper oxide and copper chromate phases that were seen in the XRD patterns were determined by using D/Scherrer equation. And we also have done the H2TPR experiments, which is crucial for this particular reaction. I will tell you in detail later. And we also have estimated the surface acidities of these catalysts by TPD of ammonia. And we also have done the estimation of surface copper by N2O titration, which is the best technique to estimate the surface copper species which are present on catalysts. So then, when these catalysts were subjected to cyclocondensation of this particular reaction using 1,2-propiondiamine and aqueous glycerol, you can see that a particular composition of Cu2Cr1 is showing higher activity and higher selectivity. As a result, the rate of 2,6-dimethyl-pyrazine was 383 moles per gram per second multiplied by 10 to the minus 8. This is the rate which we have mentioned. Whereas a chromium-rich compound, that is copper-1 Cr3, has shown very low rate, that is 40. So then, what are the reasons then which are causing to get a particular catalyst system is showing a tremendously high rate of a given product, and the other hand, the other one is showing inferior activity? These are the rest of the catalyst systems are to understand the mechanism and to understand the surface structure of these catalysts. And when I try to see that, when I try to correlate all these catalyst systems using the N2O titration data, this particular catalyst system Cu2Cr1 was showing a better performance towards the 2,6-dimethyl-pyrazine synthesis compared to others. So then, the catalysts were characterized by all these techniques like XRD of fresh catalyst, calcined, and reduced catalyst. You can see that reduced form of catalyst shows copper metal, copper chromate, and Cr2O3. And similarly, fresh catalyst shows oxide form of copper oxide. And when we see the analysis of FTIR of the fresh and reduced catalyst, here I just want to stress one important point, that we could see here this 934 vibrational band is due to Cr double bond O asymmetric stretching, which is due to the presence of chromium in higher oxidation state, that is Cr6+. There could be a possibility when you synthesize mixed oxides or spinels of these metal chromides, there is a chance highly possible that you will have higher oxidation state of chromium, which is clearly seen in the FTIR analysis. After reduction, that peak is disappeared, which means that whatever the Cr6+ is present in the fresh calcined form were reduced to Cr3+, because that is the most stable form. And when we reduce these catalysts at 450 degrees centigrade, it is unlikely that Cr6+ goes to Cr0, because it requires more than 1500 degrees centigrade to get the Cr0 valence state. So these catalysts were subjected to TPR analysis, which is essential to understand the, what you call copper chromium interactions. What we also understand from this is the Tmax. The Tmax is the one which the temperature at which a particular catalyst is undergoing complete reduction. If you can see that from A to G, A is pure copper oxide and G is the pure chromium oxide. This is keep on increasing the chromium loading. When you are increasing the chromium loading, the Tmax is shifted towards higher temperatures, which indicates that there is a strong interaction between a copper and chromium in the form of spinels. The essential part of the TPR analysis is that the catalyst systems, what we have tested for this particular reaction, I have to reduce this catalyst for one reason is that to convert the Cr6+, which is present in calcined form, to Cr3+, which is more stable under water. Reason is that all the catalyst systems what we have tested for dehydrocyclization of this particular 1,2-PDA and 1,2-propanediamine and glycerol consists of what you call 10 to 20 weight % glycerol and 80 weight % of water. In presence of water, there is a possibility that if at all there is a chromium 6+, which will be which is water soluble. As a result, the chromium catalyst gets leached, so that there is a collapse in catalyst structure as well as the loss in activity that will happen. So is the reason why we have to reduce this catalyst, and the TPR gives a precise analysis. So then, since I mentioned that this reaction proceeds on both acid and basic sides, you can see that four best catalyst systems were what you call analyzed by TPD of ammonia. You see that A is this particular, this is a copper oxide, the top one is copper oxide, and this is copper 2 Cr1, and this is chromium rich, C is a chromium rich compound. Chromium rich compound, presence of higher amount of chromium obviously shows higher amount of acidity, and the last one is the bulk chromium oxide. So using these acidity data and the data which we have obtained from N2O titration, we were unable to correlate the activity of the catalyst systems that were showing, some show inferior activity, the other shows better performance. And then we try to, analyze the type of acid sites, whether it is a Bronsted acid site or Lewis acid site, or otherwise a Bronsted base or Lewis base. Then we check the literature with one of the paper that was published by Guido Busca, which shows that you will have 4 combinations of mixed oxides. One is ionic oxides, covalent oxides, and a kind of silica aluminous and protonic zeolites that will possess a Lewis acid sites and Bronsted acid sites, and higher oxidation state metal oxides such as manganese, chromium, and etc. So the interaction, when you try to adsorb pyridine or 2,6-dimethyl-pyridine, these are the 2 probe molecules. Pyridine is a base, and presence of a metal cation, that is Lewis acid, there will be an interaction between the lone pair electron of pyridine with the Lewis acid site. This will appear a peak in the IR spectrum. When you adsorb pyridine on the catalyst surface, you will find a fundamental band at 1450 inverse centimeter. On the other hand, if there is an interaction between proton, which is Bronsted acid, when you adsorb pyridine, the fundamental band will appear at 1540. Just try to remember this. What is the advantage of having probe adsorbed IR technique? That will give you type and nature of acid sites present on the catalyst surface, and the strength of interactions, a relative proportion of acid sites, and stability of acid sites. This depends on the spectra which shows these fundamental bands. So for that, what is required is a Harrick cell, which is a specially designed Harrick cell with which we can go for in situ probe adsorbed IR analysis of different solid materials. When you look at the reaction mechanism that I was explaining, this reaction proceeds on both acidic and basic sides. If the reaction proceeds on first acidic sides, it will form hydroxyacetone. And if the reaction proceeds initially with the basic sides dihydroxyacetone, in any case, these two, undergo cyclocondensation together to form this particular molecule, and piperazine, 2,6-dimethyl-piperazine, and this will undergo, alcohol kind of saturated ring. What will happen is that when it reaches this particular portion, what is required is to further convert this particular alcohol into high selective 2,6-dimethylpyrazine. A combination of metallic copper and copper chromate is required. The samples what we have tested, the best catalyst system with Cu2Cr1 was showing high selectivity towards higher rate towards this particular compound is because of it contains high metal surface area, which we have seen by N2O titration, and the presence of copper chromate species. On the other hand, the chromium rich compound was showing less amount of surface copper, and predominantly it shows the just acidic component of Cr2. So is the reason why we were unable to get what is called that particular compound in less ratio. The other reason what I want to emphasize here is that this particular alcohol, presence of enough number of basic sites, this will easily undergo to form the desired compound. So what we have done a range of catalyst system. All those catalysts were tested, but I am just taking for convenience sake the best catalyst system and the catalyst which is showing inferior activity. The copper rich spinel was showing 90.8% selectivity with such a conversion, and the rate was so high, and the chromium rich was showing 40 to rate, which means that the copper-rich compound was showing more than 9.6 times higher, which is close to an order of higher activity in terms of the rate of a given compound. Then what we see is that if you look at all these physicochemical characteristics of these catalysts, you see that the N2O titration data here 78 moles micromoles per gram of catalyst was found from a copper-rich compound, whereas the chromium-rich compound was showing very low, that is 28.9. So what we try to understand from this data is that when you subject pyridine over these two catalyst systems, for example, chromium-rich and copper-rich, you can see the fundamental bands at for around 1450 region. This is due to the Lewis acid sites, and the 1540 is due to the pyridine which is interacting with bronze acid sites. Here you can see the pictorial presentation is repeated here. You see that the band ratios, when we try to quantify these using the Km function, and we could see that a high ratio of Lewis acid sites present on chromium-rich compound, and a very small number of Lewis acid sites were present on the copper-rich compound. On the other hand, the bronzed acid sites were more or less similar. When we made a what you call the spectra were integrated, the band peak widths were integrated, and we could see that the bronzed acidity ratio on copper-rich to chromium-rich was 0.9. And similarly, these results were in good relation with the XPS data, that where we can see that the copper-rich to chromium-rich was showing close to 0.6. And both samples have shown bronzed acidity, but this particular catalyst was showing tremendously high activity and this was showing lower activity, which means that having both the same strength of bronzed acidity, catalysts, we can say that there is no role of bronzed acid sites. On the other hand, you have a strong Lewis acidity here, and marginally lower Lewis acidity was found with the copper bromide catalyst. Since this reaction is a combination of both acid and basic sites along with metallic copper, then what we try to do is that we did not get any conclusion from the IR observed analysis. Then what we did was that we intentionally poisoned the catalyst during the course of reaction, since pyridine adsorbs selectively on the which will on both bronzed and Lewis acid site. This is bronzed acid site, and it can also reach a metal cation where it can interact with the Lewis acid site. On the other hand, 2,6-dimethyl pyridine will selectively adsorb on the bronzed acid sites, and it cannot reach the metal cation due to the steric due to these particular two hydroxyl groups. So what we have done is that during the course of reaction, we have intentionally added some pyridine. So before adding the pyridine, when we started the reaction, the conversion was 72.5%, and this is also 1:1 molar ratio is required to get the product distribution. And when pyridine was added, pyridine covers both bronzed and Lewis acid sites. The activity was drastically decreased to 21.4. And then we have regenerated the catalyst, just stopping the feed and going up to 400 degrees centigrade in nitrogen flow for a couple of hours in steam. Then we could regenerate the activity. Whereas if you try to poison the catalyst with 2,6-dimethyl pyridine, the activity was from 71.8 to it was decreased to 57.6. And the decrease in conversion was very low when you try to poison the catalyst with 2,6-dimethyl pyridine, which is a selective poison for bronzed acids. Whereas when you try to poison the catalyst with pyridine, which covers both bronzed acid site, and the activity was drastically falling, which means that the role of Lewis acid sites on this particular reaction. Then, as I mentioned, this reaction will also, what is required is basic sites. A suitable probe molecule to analyze the surface basic sites of these catalyst systems is formic acid. When we try to see the formic acid adsorbed IR spectra, you see that copper, this is a chromium, bulk chromium oxide, this is a bulk copper oxide, and this is a chromium rich, and this is the copper rich compound or spinel, wherein the 1620 band is due to strong interaction of formic acid with the strong basic sites, surface basic sites. And these two bands, 1584 and 1677, are due to the decomposition of surface formate species, and 1752 peak is due to the weakly adsorbed formic acid, or formic acid that is weakly interacted with the weak basic sites present on the catalyst system. If you can see that this copper-rich compound has got a strong presence of strong basic sites when you compare with the copper oxide and chromium oxide, as well as the chromium-rich copper chromite catalyst system. So this shows that presence of strong basic sites on the copper-rich compound, whereas the chromium-rich compound was showing a very weak ratio. It was very difficult to what you call estimate, quantify the peak intensities, because these were all broad peaks, and we have done the what you call these things simulated, and it was difficult to estimate the peak intensity. So then what we have done is that we try to correlate with the full width of maximum of these peaks. Remember, these are all normalized spectra. These spectra were not independently collected, and the y-axis is normalized. So in normalized spectra, you can also compare the peak intensities of these particular catalyst systems. You can see that I am showing these particular mechanism route wherein basic sites are required to get this particular catalyst system, wherein copper-rich compound was showing higher rate and the chromium-rich compound was showing inferior rate, which is an order of magnitude lower than this particular system. Then what we have done is that these two catalyst systems, again, we subjected these to different temperatures. The reason is that when we have done this particular, this spectra was collected at 120 degrees centigrade, just to avoid the moisture first of all. Then, in any case, all these catalysts were analyzed by probe adsorbed IR spectroscopy at 120 degrees centigrade initially, and then we have done it 150. You see that this particular spectra is a chromium rich and this is a copper rich. Just to rationalize and clearly understand what is happening on the the surface basic sites, we can evaluate by, for example, 150 degrees centigrade spectra shows this particular one, and keep on increasing the degassing these particular catalyst system at about 300 degrees centigrade. You see this pink spectrum is due to the spectra that is collected at 300 degrees centigrade degassing. And here I must mention that in IR spectra we have seen before, the fresh calcine samples have shown 934 peak, which is due to the presence of chromium 6+. So when we loaded the fresh catalyst system in the IR cell, this is a fresh catalyst system, and after reduction, these peaks were disappeared. You see that the orange color spectrum here, absence of any peaks due to CR6+, which means that all the CR6+ were converted to CR3+. Similarly, copper-rich catalyst was subjected to formic acid adsorption. You see that similar thing happened, that the peak intensities were decreased due to the desorption of formic acid or formates, or decomposed formate species like CH, C double bond O, symmetric and asymmetric. 4 bands are there. These bands are disappeared, but you see the stability of this particular copper-rich compound. You see that this is the pink color one is showing higher intensity compared to the chromium-rich compound. So, which means that we try to work out, we try to collect these spectra at slightly elevated temperatures close to the reaction temperatures. So, this shows that the role of what you call basic sites. But still we do not know what kind of basic site. Is it the Bronsted base or Lewis base? because this particular metal chromides or a mixed oxide combination of copper and copper chromite will have a varied range of what you call surface species. Reason is that chromium exists in different oxidation states, and this typical behavior of chromium tries to change its structure when you expose this particular catalyst system even ppm level of oxygen. So we try to analyze these particular catalysts by absorbing the water on this particular chromium rich and copper rich catalyst. Reason I will tell you, if you want to understand, if you want to know which kind of basic set, whether it's a Lewis base or Bronsted base, then these two are the envisaged, expected or possible basic sites present on the catalyst surface. When you try to adsorb formic acid, for example, on the Lewis base, then this will form the surface formats were seen. In either case, we will see the surface formats. But what we will see is that the metal cation coordinated with the OH minus. And when we try to see the spectrum, that is the formic acid interacted with the MOH minus, this should form M cation plus coordinated with water. Then how do we know? We cannot know from these spectra of the metal cation interacted with the water molecules. Then what we have done is that under similar experimental conditions, these two catalysts, one is chromium rich and the other one is copper rich catalyst, fresh catalyst was loaded, reduced, and a dose of 5 millimole of water was absorbed at 150 degrees centigrade and flushed at different temperatures in nitrogen. But both of these samples have not shown the presence of metal cation coordinated with water, a band that appears at 3550, which means that we can perhaps say that these kind of species were absent on the catalyst surface, and the species like metal cation with Lewis base were present on the catalyst surface, since this particular species were absent. And when we try to adsorb the water on the reduced copper, it is unlikely that this metallic copper will undergo copper oxide plus hydrogen, because this is virtually impossible at a temperature of 300 degrees centigrade to get hydrogen when you subject steam onto the reduced copper surface. Whereas mixed oxides of zinc or chromium, when you subject the reduced form of these these phenols after steam exposure, they may undergo kind of form of HOMX plus OH kind of species after the adsorption of water. So then the absence of metal coordinated IR band was seen in both of the cases, which means that we can possibly say that presence of Lewis basic sites are acting for this particular reaction. So from these studies, what I can conclude is that when we tested all these metal chromite catalyst systems for synthesis of 2,6-dimethyl pyrazine, all the metal chromites have shown some activity, but copper chromite have shown tremendously high activity. And as I mentioned, it requires a pair of acid-basic sites to get the desired compound at higher rate. And what we found was that the presence of strong acid sites and mild basic sites produced the 2,6-dimethyl piperazine, whereas pair of strong basic sites and higher number of surface copper metal sites leads to the higher rate of 2,6-dimethyl pyrazine. So from these studies, what we can do is that if you can clearly understand the surface structure of the catalyst using a combination of IR, probe adsorbed IR, as well as different characterization techniques, XRD, maybe IR, those are all bulk techniques, however, but you have an advantage of having the estimation of surface metallic copper by NO titration technique. If you can fine-tune the surface structure, then you can also fine-tune the product distribution to some extent. So my second example is on the conversion of levulinic acid to gamma-valolactone. As we all know that biomass is a desirable alternative for the production of fine chemicals because it is sustainable and often low cost. And the levulinic acid is expected to become a major renewable feedstock because of several reasons. So studies pertaining to conversion of carbohydrates, for example, biomass carbohydrates to produce a set of platform chemicals, for example, levulinic acid conversion to gamma-valolactone, as levulinic acid was viewed as a feedstock for the production of this particular gamma-valolactone, which is having the advantage of having this particular compound is that it is a high boiler, transportation is easy, and about 20% of GVL, gamma-valolactone, can be blended with diesel. So the other advantage of having this molecule is that this is also a food ingredient. Somewhere it is being used as a food flavoring agent. So this part of the project under 12th 5-year plan, when we started, this portion of the work was taken up by chemical engineers, and we were working on levulinic acid to gamma-valolactone, and further we have extended further conversion of gamma-valolactone to valeric acid, which is more has got a high commercial value than the gamma-valolactone. So then, if you look at the historical perspectives for the last 30 years or 40 years on biomass conversion processes, wherein if you start with, for example, I will tell you here, the levulinic acid, what we could get is from biomass that contains some amount of water. There is no sense if you work with pure levulinic acid to convert pure levulinic acid into gamma-valolactone. What is viable is that the levulinic acid which is expected from a biomass process that contains impurities as well, such as water and other compounds like formic acid, which is about 28% is present in the stream. So then, whatever the source that you start with, any source, any industry that they provide you, the crude levulinic acid contains large amount of water. So initially, we try to examine the role of the water on the particular catalyst system. Then we tried with ruthenium supported on carbon. Then we see when pure levulinic acid was subjected with hydrogen. What we could see is that this particular alpha angelicolactone was 95%. This will be formed by dehydration of this particular molecule. Whereas when you subject the same molecule in presence of water, it was showing a high selectivity towards gamma-valolactone. Then we try to see the nature of this particular catalyst system by pyridine-adsorbed IR spectra. It shows, this particular catalyst shows under hydrogen reduction conditions, it was not showing any peak. This is Lewis acid sites, and the peak at 1540 is due to bronzed acid site. And the reason for getting this particular compound in high selectivity is due to the presence of bronzed acid site. This is how we rationalize this particular one example. So then later on we move to a non-noble metal by screening different catalyst systems like ruthenium. These are all noble metals, and just to compare a catalyst system, orbitally we fixed 5-8% of metal loading on these catalyst system. When we tested these catalysts for this particular reaction, surprisingly, this particular catalyst system was showing high selectivity, although the conversion was lower compared to the other noble metal catalysts. And we then moved on to vary the loadings 5, 10, 15, 20, 38%, wherein we could see that this particular 28% catalyst was showing high selectivity and higher conversion compared to the other catalyst system. Then we try to see the physicochemical characteristics of these catalysts, wherein we see that a slightly higher metallic surface area of nickel was present on 28% compared to others. In any case, the 1.89, 1.9 was similar to 28% of this catalyst system. And then when we tested these, when we analyzed these catalysts by TPR analysis, you can see that there is a peak shift towards higher temperatures if you keep on increasing the nickel loading. is an indication of the bulk property of TPR analysis when you subject it to these catalyst systems for conversion of levulinic acid to gamma valolactone. As I mentioned earlier, this reaction proceeds firstly by dehydration and forms a cyclic alpha angelica lactone. This will be further reduced to form the what you call gamma valolactone. What was required was that a kind of a Lewis acid site and metal. And then when we try to analyze this particular catalyst system, the best one and the inferior one, what we could see is that the clumsy pattern of pyridine adsorbed IR spectra. So we could not get a better result. Reason is that we must remember that the titania possesses more than 90% of Lewis acidity. The Bronsted acidity on this catalyst is very, very low. So the spectra was showing clumsy. Then we moved to what you call the kinetic studies, wherein varying the surface, support materials. When we subjected, 28% of nickel on silica, gamma, alumina, and zirconia. Silica is more or less neutral. Zirconia possesses acidity, and gamma, alumina has got both acidic and basic sides. When we try to estimate these particular supports for, with 28% nickel, we could see that the silica possesses Bronsted to Lewis acidity less than 0.1%, whereas alumina and zirconia possesses Bronsted to Lewis acidity ratio greater than 0.2. I'm not showing here any IR spectra of pyridine adsorbed, what you call IR spectra here, because you understood clearly now by now. So this shows that the presence of mild acidic sites, the selectivity towards gamma valolactone is higher, whereas valeric acid and angelica lactones were very low compared to the support which possesses higher acidity was showing slightly better selectivity towards valeric acid. You can see that when we try to estimate when we try to make a graph over BAS ratio, BAS LAS ratio against selectivity towards gamma valolactone and the ring opening counts. I must tell you here is that the formation of valeric acid, which is a more important compound than the GVL, started, we could start seeing this particular compound during the course of these experimental results. Then we realized how these ring opening products were formed, which is due to the ring opening of gamma valolactone leads to this pentanoic acid. This will subsequently undergo hydrogenation to form pentanoic acid. Reaction proceeds on acid sites, a metal site. Again, it will undergo cyclization, hydrogenation, and what you call ring opening, and further hydrogenation to form a pentanoic acid. So what is happening is here that when we try to modify the nickel-based catalyst systems with varied promoters and all, in the absence of a promoter like tungsten oxide, you see the product distribution. The rate of GVL was so much so, and the valeric acid was very less. And when the same catalyst was at certain loading of tungsten oxide, was showing tremendously high rate of valeric acid compared to the absence of tungsten, absent nickel titania catalyst. Then we try to see what is happening. You see here the presence of Bronsted acid sites are so high on tungsten oxide modified catalyst system when compared to the simple nickel titania. As I mentioned, this particular nickel titania, if you see that whatever if at all if there is any Bronsted acidity, please remember that titania is not going to contribute any Bronsted acidity. You see that huge amount of Lewis acidity is present on this particular catalyst system. When you modify this particular catalyst system with tungsten oxide, you see there is a Fermi resonance, a shift in what we call the fundamental band of this particular Lewis acid site, which appears at 1450, is dramatically decreased, and it is also shifted towards a higher wave number. Then we try to see the interaction between tungsten oxide and nickel clearly in the H2TPR analysis of these catalyst systems. If you keep on increasing the tungsten loading, you see that the Tmax was going towards higher temperature, which means that when a tungsten oxide like a species are in close proximity or close contact with the nickel oxide species, that will prevent the reduction of nickel oxide species. As a result, what will happen is that this will form under the reaction conditions. What we have seen from the pyridine observed spectroscopy, that the TOF was in direct correlation with the tungsten oxide on over a particular support material. The mechanism, how we could define the role of this particular proton was the hydroxyl group present on the nickel oxide species, which could contribute, which can drag this particular beta proton. As a result, this particular gamma valprolactone ring was opening from the pentanoic acid. This we have published recently in Applied Catalysis CA. So again, what we have done is that we have tried to poison the catalyst system just to see the role of Lewis acid sites as well as the Bronsted acid sites. Before the addition of a probe, that is pyridine, in fresh conditions, the conversion was 29.9. When we observed pyridine when we injected the pyridine in a successive injections along with the stream, there is a drastic reduction in conversion of levulinic acid, and after regeneration it is almost retained, but the conversion levels were fallen by 20. Here, when you try to poison the catalyst with the 2,6-dimethyl pyridine, the conversion was marginally decreased, and it is also almost retained also. Which means that when you try to block the Bronsted acid sites, the conversion was little fallen. When you try to block the both sides, for example, the Lewis acid sites as well as the Bronsted acid sites, the activity was fallen to very low conversions. Which means that presence of Lewis acid sites as well as presence of what you call metal in conjunction with the metal ion. It is virtually difficult to define whether it is, for example, if a cluster of NiO is present on the catalyst surface. NiO is nothing but Ni2+. I may say that it's a weak Lewis acid site, nickel 2+. On the other hand, O2, if O2- is there, it can be a Lewis base. It is a Lewis base, right? But I cannot say that whether it is strong or weak unless I see the probe observed what you call IR spectra. Then we try to see, modify with other group 5 elements, the large, what you call higher oxidation state containing species. We see that there is a enhancement in the formation of valproic acid, and when you have an acidic component of niobium type of metal was modified, then we see that a lower amount of this particular compound was formed. So this, you see that how we, using the data of probe observed IR spectroscopy, we can be able to say that presence of Lewis acid sites and metallic sites, this particular valproic acid is low. Whereas if you have a presence of Bronsted acid sites and ionic nickel is obvious. When the tungsten oxides type of species are interacted with the nickel oxide species, it requires higher temperatures because the oxygen supply is continuously on from the tungsten oxide, or otherwise there is a strong interaction. So the interacted species of nickel oxide and tungsten oxide species reduction takes place at high temperatures. Usually we reduce the catalyst at constant temperature like 450. So what it requires is that I have shown in this particular here that you see we reduce the catalyst at 450 degrees centigrade. But still there could be existence of ionic nickel species. Those species were also involved in the reaction to produce to some extent higher amount of what you call valproic acid. And what we were trying to do is that when we try to synthesize gamma valprolactone from levulinic acid, we could extend it to valproic acid, and further the studies are on using the levulinic acid that contains formic acid. So we are not going to use any external hydrogen, and we want to use formic acid as a hydrogen source that will generate in situ hydrogen. When you subject formic acid over a basic nature catalyst that will form you CO2 plus hydrogen. If you subject formic acid over acidic catalyst system, that will give you, carbon monoxide and water. We are trying to see the effects of, presence of formic acid in the levulinic acid stream on the product distribution. So then we just tried with several modifiers, and some results are in press. So with these results, what I want to summarize here is that hydrogenation of levulinic acid to gamma valolactone requires, firstly, an acidic site is desperately required just to convert the levulinic acid into anglical lactone. Then the rest of the hydrogenation part takes place on a metal site, especially when we have seen that nickel site. And what we can see from the drift spectroscopic studies is that we are able to see the strength of Lewis acids and bronze acid sites and how they are going to influence the what you call the product distribution, whether it is gamma valrolactone or what you call valeric acid. So similarly, as I mentioned earlier, the product distribution can also be fine-tuned if you understand clearly the surface structure of the catalyst by using the other techniques like XRD, TPD of ammonia, and what you call other titration techniques like N2O pulse titrations. So what is important is that to understand the bulk and surface structure, just not Roberts or IR technique can give you precise conclusion wherein these particular sites are required to get the desired products. So with these, I want to thank my director and the convener EMEEA Sadhana Railu Madam and Dr. Raja Krupadam and CSIR for NEERI and 12th Fire Plant funding. And last but not least, Dr. S. Shivaram, who was our steering committee chairman during NEERI program. Thank you for your attention. And also I thank all my students who have relentlessly worked in generating the IR data as well as the kinetic data just to publish in different journals. Thank you so much. If you have any questions, I'm ready to answer.
Thank you, Dr. Venugopal. You are given a very nice and wonderful presentation. It is a truly an academic, as well as you have done a very detailed investigations and mechanism. I think I have seen this type of presentation very first time where the mechanism was probed very thoroughly by using infrared spectroscopy. So I'm really happy to see such a very good presentations in this inaugural webinar series. So I request if any of the anybody have some questions to
Sir,
Dr. Venugopal, please.
Sir,
Dr. Pratap Reddy?
Yes, sir. Yes, sir. Sir, actually, I would like to say my sincere thanks for my actual co-guide. Dr. Venugopal sir is the co-guide since 2001 to 2006 for my doctoral thesis, and I learned from him the basics of the catalysis for the applications of the water technology, wastewater treatment technologies, and air pollutions during my doctoral and postdoctoral degree. And as you told just now, how basics he is explaining, once you understand that the acid-base sites, how can we manage with the metals and metal oxides on the surfaces? These I thought from my basic degree during the doctoral degree, while doing a research article that silver hydroxyapatite for the disinfection of the bacteria. And he has taught at the time itself the in situ IR to me. And these are all basics since today. It was all giving the basic support to me wherever I go and apply for all the current knowledge to apply for the environmental applications for the water treatment technologies and even in air pollution also. So I would like to say once again, I am very happy to interact with the sir. Along with even Dr. Krupadam sir is also a teacher for me for my master's degree for the environmental science and technology in JNTU. So
I think Giri Venkatesh has he has raised his hand, Giri Venkatesh.
Yeah.
Let him ask a question.
Okay, sir.
First finish, ready. You can finish and then we can go for your...
You have any question?
Yes, no, sir, actually. Yeah.
Okay.
Yeah.
Let's discuss with other colleagues.
Hippargi.
Raised his hand.
Hippargi.
Yeah.
Yeah, you can ask question.
Thank you, Gopal sir. That actually lecture is very nice. Actually, we have heard lot of. Actually, we are working on the materials, but actually, how they have to use in organic application. So we have learned today. So there is inorganic and organic both studies are there. Sir, thank you very much. But I have one two questions that actually in the first reaction you have shown. There are multiple organic reactions are there. Okay. Multiple steps are there. Multiple functional groups are also there. So how you are analyzing that actually at each step? How you are analyzing that actually it is converting into that? Actually, IR only shows the functional group. Okay.
No. Yeah. Please continue.
No, but actually that's like OH conversion that NH2. That conversion how that actually TLC is not sufficient and IR I think that functional group IR is only shows functional group. Sometimes there is breakage of aromatic groups also possible.
Right.
So in that case, how you are doing that?
Now I'll tell you. See, these the IR spectra is just to define the surface species, not the product distribution. The conversion selectivities were all done by GCMS and NMR spectroscopy.
Okay.
This is a fixed bed continuous reactor. No, we pass the substrate from top and at the bottom we collect the products, right? Okay. Yeah. So we have done it by GCMS and NMR spectroscopy. On the other hand, the question pertaining to the IR studies, IR studies are it's a kind of the reaction studies in IR cell is also possible. People are also working, but 100% we have not done it for several reasons. One reason is that when your substrate or the starting compounds are low boilers, no issue. For example, CO oxidation or water gas kind of sort of reactions can be easily carried out in IR cell. But the dirty molecules like pyridines and picolines and pyrazines, it's difficult to handle in IR cell. The post, after the reaction, it's very difficult to clean the IR cell. So we don't use it to monitor the reactions in IR cell. Okay. So the data what I have shown is probe absorbed IR. But the rest of the data, I just quickly passed on not to confuse you people as well as not to get confused myself. So I have just give a glimpse on, I've taken some numbers, selected numbers just to, explain the best catalyst system and the inferior, the catalyst which is showing inferior activity. Otherwise, we will do it with the GCMAS and NMR. Product confirmation and all done, pakka.
Okay, sir. Thank you, sir. Thank you.
So if the questions are not there, then so we are very thankful to Dr. Venugopal, who's given an excellent presentation where how can be desired products can be formed and how we cannot get the designed product at certain cases. So it's a wonderful lecture. Thank you, Dr. Venugopal, for attending this webinar and giving a nice presentation. So thank you very much.
Thank you,
sir. I think now we can move to the vote of thanks for this afternoon session. I think I am supposed to do it as per the sorted the program. So the afternoon session, the first inaugural lecture, this is the second inaugural lecture of the day, is given by Professor Deepankar Das Sharma. It is a very fortunate for us having such a top scientist, physicist delivered a lecture on how materials, perovskites can be used as a photovoltaic materials. And sir, I am very thankful for you to enlightening us about the perovskite material is a wonderful material based on the structural properties, and I'm very thankful for you. And you are given a very wonderful basic understanding of the mechanism during the photovoltaic emission properties and related properties where the molecules inside can move, how it affects the energy picture. So, Professor Sharma Sab, I'm very thankful for you for attending this and delivering the inaugural lectures too in this webinar series. And I'm also thankful to Dr. Gopal, who is the guest lecturer today. He's given a wonderful presentation related to 2 case studies we has carried out during his project tenure, and how catalysts can be used and how we can probe the mechanism by using the infrared spectroscopy. So I'm thankful to both the speakers, and I'm thankful to our director, who is the guiding spirit and guiding strength for us to carry out this webinar series. And Dr. Rayulu madam, she is our guide and mentor who sorted out the entire program, where we are very thankful to you, madam, for this your valuable suggestions and guidance. And I'm thankful to all my colleagues in the Environmental Materials Division, Dr. Nagababu, Dr. Wagmare, Shilpa, Engineer Shilpa, Dr. Hipargi, Dr. Reddy, and Suhasini Hore. So I'm thankful to all these team members who are really supported one way or other to organizing this webinar. And the project fellows and research fellows and postdocs who are really participated in these lectures. So I'm thankful for them. Particularly Ankush, who is done an excellent job in conducting these proceedings online. He is the key person who take care of these entire online proceedings. So with this, we are closing this webinar series 1, and I hope that everybody enjoyed this, and particularly who are the participants. There are around 400 participants on the online. So I'm thankful to the all participants. I hope that they enlightened with the new knowledge and new science from the expert presentations. So with this, I conclude the session, and I declare that the webinar 1, series 1 on emerging materials for energy and environmental applications is closed now. We'll meet in the next series. Thank you very much. If I miss somebody during vote of thanks, kindly pardon me. So with this, I declare that the webinar is closed.
Thank you, sir. Thank you.